Yeah, for anything.
Yeah.
You never know what's going to happen.
No, you just slap on some sunscreen.
Okay, I think my recording is going now, so we'll hope for the best with that. Thanks for coming, guys. Good to see you. Haven't written the test yet, so we're kind of winging it from that point of view, but I hope that by now everybody kind of knows what they're up against. We've got 4 chapters to look at. Chapter 6, mainly the kernel and the range of a linear transformation and the relationship between them. So we have a relationship through the dimension equation, right? The dimension of the kernel plus the dimension of the range equals the dimension of V. So that general rank nullity theorem, really important, so you'll find that in the review packet. And then in addition to that, there's the concepts of one-to-one and onto transformations, and those are very simple definitions, but sorry, we have a space in the middle here, but we're going to have kind of 2 paths to the room, just so my camera can work. So one-to-one and onto, and being able to assess whether you have a transformation that's one-to-one, onto, both, or neither. Being able to do things like that. And I've got videos. Actually, that was when I had been gone. So I made videos. I had videos, and they're still up there. So you guys can always watch those examples again if you feel so inclined. Chapter 7 is a really important chapter from the point of view of tools, because you learn in chapter 7 all about finding eigenvalues and eigenvectors, diagonalizing a matrix, and sort of what that's good for, and finding bases for eigenspaces, and so on and so forth. And as we saw later, that comes into play in chapter 9 when we go back to looking at systems of differential equations again. So chapter 7 is really a chapter of tools that you then will be using in many applications, in particular in chapter 9. Chapter 8 is where we took a big deep breath and took a break from vectors, and for the most part matrices didn't show up there either, except for the Wronskian. That's the only matrix in chapter 8 really. And what you're doing there is you're just solving higher order differential equations. And there's sort of a 3-step process, right? You first solve the homogeneous differential equation, right? There's a dimension to that. That's solution set forms a vector space whose dimension agrees with the order of the differential equation. So if I have a 5th order differential equation, then any basis for the solutions to that differential equation would have 5 vectors in it, right? So you find this sort of general solution. We ended up calling it the complementary function, which is where you're solving this homogeneous differential equation and writing down the general solution. Then the second step is to find one particular solution, and it's something that did not quite resonate with everybody on the quiz that we took a week ago, which is you have to be able to decide whether to use annihilators or variation of parameters. And one of the best ways to decide is to simply look at the right-hand side of that differential equation, because if the function that's there is not in the form of something in your annihilator table, well, then you can't use annihilators, right? Similarly, if your differential equation is higher than 2nd order, I promised you I wouldn't ask you to do variation of parameters on anything of order more than 2. So there's some clues as to which way to go about solving these things that you can get. But then you need to be able to do the annihilator method and do the variation of parameters method. I may hit that chapter a little lighter tonight than the other things. Usually I find that people have an easier time with it. It's not quite so notationally heavy, and it's a little bit more plug and chug, kind of grind through some calculations. But if there's questions, we'll go over that. And then finally, chapter 9, which is where we kind of start putting everything together. We're solving linear systems of differential equations. And we can have a coefficient matrix that's defective or non-defective. We might have eigenvalues to that matrix, that coefficient matrix, that are either real numbers or complex numbers. So different scenarios that can come up. In the case of a 2 by 2 linear system, we even drew pictures of the solution set, and those pictures would generally, they're what we call the phase portrait, and there were sort of 6 different classification types for this phase portrait depending on the eigenvalues, right? So I want everybody to be familiar with that because it's a nice way to understand what's really going on visually when you're solving a 2x2 linear system. And then, of course, other than that, there's just the whole business of finding the eigenvalues and eigenvectors, writing down the solutions. In some cases, you have to deal with complex numbers and sort of floy your vector solutions out. In other cases, you have to do these W vectors in the case of a defective linear system. So there's a variety of things that can come up. We probably won't do an example of absolutely everything tonight, but we're going to do quite a few examples. So that's just a really quick overview. Again, the review packet has a checklist of all the things that you really should make sure you know how to do, and you know, a lot of practice problems as well. I would suggest doing the sample final probably tomorrow or something. You know, as kind of a check how you're coming along with things, and then yeah, don't forget I have a lot of office hours between now and Monday, so there'll be chances to ask questions. Yes.
Would you mind just mentioning, like, is there kind of a succinct difference between chapter 8 and chapter 9?
The difference between chapter 8 and chapter 9 is substantial. Chapter 8 is not looking at a system of differential equations, but just one single differential equation. So everything in chapter 8 is scalar function based, right? You're not solving for any kind of vectors there. You're just solving for the scalar solutions to your differential equation. Chapter 9 is about systems of differential equations. So in chapter 9, of course, what you're going to see a lot of is vectors to represent those solutions, right? So you'll have vector solutions, and so it's a little bit more notationally heavy. Okay, I would say about 25% of the exam on each of those 4 chapters that I just kind of overviewed briefly. And within that, you know, you will see a few more like conceptual type questions. I mean, there's going to be some problems that are going to be just like homework problems, except maybe with the numbers changed. But there's also going to be some questions that may be a little different than exactly what you ever saw before. Not because I'm trying to like make you figure something new out on the fly, but rather I want to see if you can use your tools, if you have enough of a mastery and comfort level to maybe apply them to something you haven't quite seen before. Okay, so I'm going to basically spend our time today doing a bunch of practice problems. I actually went back to last semester's materials that I had, and I looked at the quiz that I gave a semester ago it was basically like your quiz 3, and I actually thought these were some good problems. So maybe before I jump into the review session questions, because these I've already posted, if we don't do every single thing on here, it's not the end of the world. Maybe I'll start with some of these. So these are sort of from what I guess we could consider a mock a mock quiz 3. So we all took the real quiz last Monday, and you have the solutions to that, and hopefully you've looked that over again. But here are some you know, additional problems that are maybe useful to think about as well. I'll label these problems with letters instead of numbers so we don't confuse this with what's in the review session questions that I'm going to do in a little bit. Okay, so here's an example. This is straight off of a quiz that I gave last year. Let L be equal to d cubed minus 2d squared plus 5d. Okay? And here's what this says. It says find a basis for the kernel of L. Find a basis for the kernel of L. So remember that the kernel of a function or a transformation is always a subspace. So it's always going to have a basis. Anything that is a subspace will have a basis, and they're asking us to find it. Can somebody tell me right away what the dimension of this kernel of L would be? It's just the order of the differential equation, which is 3, exactly. In fact, we could even write down the differential equation here. The differential equation, if you were thinking of it in that way, would just simply be y triple prime minus 2y double prime plus 5y prime equals 0. So everywhere you see a d, remember that's just the derivative operator, and so powers of d just represent higher order derivatives. Okay, so this is the point is this is a third order differential equation. Also, it's homogeneous. I've set it equal to 0 because I'm looking for the kernel of it, right? And you're looking for the kernel of something, you're going to set the transformation of a vector equal to 0. Okay, so how do we solve a problem like this? What would you suggest that I do? Okay, we find the auxiliary equation and then look for the roots of that. Exactly. So that's exactly what I'm going to do here. And you're going to have to stay scooched over because I've got a little alley here where I think you're okay there, but if you want a little more room, you might.
Yeah.
Okay, so let's do it. Let's go ahead and write down the auxiliary equation. Remember that you have to do this very carefully. I see people mess this up all the time. Every time you have a derivative, it gives you a corresponding r. So multiple derivatives, higher order derivatives give you higher powers of r. You've got to trust me that if I give you a question like this, then I'm going to give you something you can factor. Can somebody tell me how you would go about trying to factor this one? I would take out an r first, because every term has an r in it, and that leaves me with r squared minus 2r plus 5. Okay, and what I have in the parentheses being a quadratic, I always can resort back to the quadratic equation for that, right? So I have, first of all, I have r equals 0 over here, right? Or r equals, so I'm going to get 2 plus or minus the square root of 4 minus 20, all divided by 2. And that's just 1 plus or minus the square root of negative 16 would be what? 4i, and I have to divide that by 2, so we get 2i. Okay? So once I have my roots of my auxiliary equation, I can write down the what's called the complementary function. So that's normally what we would do is write down the complementary function. You know, you'd have c1 times e to the 0, right? That's because 0 is the first root. And then the second term would involve sines and cosines because of the complex numbers here, right? We would get e to the x times the cosine of 2x, and then c3 e to the x sine of 2x. So based on that, what would your basis actually be here? 1 e to the x cosine 2x and e to the x sine of 2x, right? And let's say that I specifically wanted you to verify that this was a basis. This would remind us of the definition of a basis. We would need to check what about these three functions?
Linearly independent.
That they're linearly independent, and how would we do that?
Be your Wronskian.
Exactly. So if I actually want you to like justify this, I'll try to be clear in my question. If you have a question about whether I'm expecting you to check linear independence during the test, be sure to ask me, but I will try to make that clear from the beginning. So the Wronskian is our main go-to tool for checking linear independence. Remember in chapter 8, the way the Wronskian works is you simply put your functions into the top row of the matrix. I'm going to need to make this bigger, a bigger matrix, I think, because when I take derivatives here, it's going to get a little bit bigger. So anyway, so this is going to end up being a 3 by 3 matrix. I just take derivatives down the matrix. So the derivative of 1 is just 0. This is going to require a product rule to take, well, this is going to be a little messy. Let's see. So you would actually have to like work this out, I guess you could say. So, alright, so if I took the first term times the derivative of the second term, I would get something like that. And then the second term times the derivative of the first term would be something like that. And then I would have to do the same thing over here. So e to the x cosine x plus e to the x sine x. Okay, so I would have that. Yes, question?
You have two signs on the left one actually. One would be-
Whoops, I probably messed the second part up. Yeah, this should have been a cosine of 2x right here. Okay, very good. So that's what you need to have. And Marilyn, I'm sorry, could you sit? I've got a camera work going on here.
sorry.
You can sit either way over on the right. Maybe that'd be definitely better. Okay, this one. So then you have to take another derivative. I think I'll skip that. The idea is what needs to be true about this Wronskian.
The determinant has to be able to be not zero for one specific x.
Right, you pick a specific x to plug into this and hopefully evaluate it and get something that's not zero. That's the idea behind it, exactly. So let's assume that we've done that. So these vectors are linearly independent, so therefore they form a basis because they're also a spanning set. Here's the whole entire solution set right up here. And clearly these three these three functions are spanning that solution set. So that's it. So we have a basis. Okay, does this make sense? Okay, so that's a great example of a combination between linear transformation material and the stuff in chapter 8 on solving homogeneous differential equations. Okay, let's take another problem off of this quiz that I gave a semester ago. Suppose that T goes from P3 of R to R7, and suppose that that is linear. Suppose this is linear, and the range of T is 4-dimensional. So suppose that we have a linear transformation and that the range is 4-dimensional, then is T 1-to-1 onto both, neither, or not enough information? So you got 5 choices here. You can tell me if T is 1-to-1, if it's onto, if it's both, if it's neither, or maybe we haven't been told enough stuff to figure it out yet. So I kind of like this problem too because this goes back to chapter 6. This is definitely a chapter 6 type of question here. So let's see what you guys have to say about that. What do you think would be relevant for us answering this kind of a question? Right, the general rank nullity theorem, right, which tells us a relationship between the dimensions of the kernel and the range. I actually mentioned it already earlier when I was overviewing everything. The dimension of the kernel of a transformation plus the dimension of the range of a transformation is equal to the dimension of V. What is the dimension of P3 of R?
It's 4.
It's 4, exactly. So this is 4. Okay, so, and we were told that the dimension of the range was 4, right? So we know that much. Just gonna make sure this is working okay before I go any further. Kind of, I'm cutting that off a little bit. Okay, I think that's okay now. So the dimension of the range is 4. So what does that tell you?
That the kernel is 0.
The dimension of the kernel is 0. And what does that tell you?
That the kernel is the vector, the 0 vector.
Right, the kernel is trivial, so what's that? What's the fancy word for that? 1-to-1. 1-to-1. So yeah, so a 1-to-1 transformation is anything with a trivial kernel. So this transformation is definitely 1-to-1. Is it onto?
No.
It can't be onto because the range is only 4-dimensional, whereas the whole W over here was R7. So remember what onto and one-to-one mean, right? Onto means the range is the whole W, which is not true here. The kernel means that one-to-one means that the kernel is trivial, which is true here. So this transformation would be one-to-one, but not onto. Okay, so that one's pretty fast once you kind of know what's going on. Okay, so far so good. Let's go on over here and do another problem. So these are problems from an old quiz that I gave a while ago when I taught the class that I didn't ask you guys, but that I think are pretty good questions. So here's another one. Let's take the following matrix A. It's going to be 4, -3, -3, 3, -2, -3, -1, 1, 2. Okay? And what I want to do here is decide if A is diagonalizable. Okay? And if so, find S and D such that S inverse AS is equal to D. So this is just like the quiz. I asked you one of these on your quiz, but this is with a different matrix. So I have a hint this time. I don't think on your quiz that I gave you a hint, but I gave this matrix a hint. So the hint is that the eigenvalues of A, multiplicities not supplied, are lambda equals 1 and lambda equals 2. Okay, so what I'm doing here is I'm trying to help you. There's no zeros in the matrix. So your characteristic equation that you would get when you take the determinant of A minus lambda I is going to be pretty messy. You're not going to be able to factor it quickly. So instead of making you figure all of that out, what I decided to do is, on this question was to sort of give people the lambdas. Except I only gave 2 lambdas. How many lambdas in total will there be?
30.
There always has to be the same number as the size of your matrix. So if this is a 3 by 3, there should be 3 lambdas. So if I gave you 2 of the lambdas, can you figure out the other one?
Yeah.
How can we figure out the other lambda? Yeah, those 2 fun facts, right? The fun facts are that the determinant of the matrix is the product of the lambdas, and even easier than that, the trace of the matrix, which is the sum of the main diagonal here, the trace has to be the sum of the lambdas. So the trace of this matrix is what?
4.
It's 4, right? And so that has to be equal to the sum of my lambdas. So I have 1 plus 2 plus one more eigenvalue that I wasn't told yet. So what does the other eigenvalue have to be?
1.
A 1, obviously. So to fill out that equation, it would have to be a 1. So we actually have the eigenvalues of 1, 1, and 2. So we can just use the trace one. We don't actually even need to use the determinant in this case. Which eigenvalue would you recommend that I use first when I'm studying the question of diagonalizability? Right, anything that repeats, which is the multiplicity, that would be lambda equals 1. Exactly. So let's look at lambda equals 1. This means I'm going to take the null space of the matrix that I get by subtracting 1 from the main diagonal. So 3, -3, -3, 3, -3, -3, and -1, 1, and 1. And all 3 of those rows are actually multiples of each other. So I can cross 2 of them off and just keep 1 of them. I'll keep the one on the bottom just because it's a little bit nicer. And how many free variables do I have?
2.
2, which means that is this eigenvalue going to pull its weight?
Yes.
It is. So actually, we already know the answer to the question here. It says, is A diagonalizable? What's the answer?
Yes.
Yes, it is. Exactly, because remember, the other eigenvalue, if it's not repeating, it will definitely pull its weight. It's only the eigenvalues that come with multiplicities, with repeats, that you have to be nervous about. And we've now checked that this eigenvalue is giving us 2 eigenvectors here. So we can do the usual back substitution to solve this. We'll use maybe y and z as free variables. And just notice from the bottom line here that the x has to equal y plus z. So x is r plus t. So the negative of x and then plus y plus z has to cancel to 0. And so if I bust out my variables, I can get my eigenvectors. When I bust out the r, I'll get 1, 1, and 0. And when I bust out the t, I will get 1, 0, and 1. Okay, so that's the v1 and the v2. Okay, great. So far so good? All right, great. And then the next step is going to be to consider the other eigenvalue, which is lambda equals 2. Okay, and so let's take a look at that. I'm going to subtract 2 from the main diagonal. And so that's going to give me 2, -3, -3, and 3, -4, -3, and then -1, 1, and 0. Okay. So we are actually going to have to take a minute and row reduce that. Okay. I think the best thing to do is to move the bottom row to the top, and of course try to put a 1 in that leading position. So I'm going to just change the bottom row to 1, -1, 0, and put it up on top. And now I'm going to try and do multiple steps at once here. I'm going to take -2 times that and add it to the first row of this matrix here. So that's because of the 1 and the 2, right? So if I take -2 times what is now going to be the top row, and I apply it to what was the top row before, I'll get my 0 right there. Okay, and then -2 times -1 is 2, and I add that to -3, I get -1. And -2 times -3 is 6, and when I add that to -3, I just get 3. Okay, and then likewise, let me take this, I mean, you could do it with this row, or you could do it with the bottom row here, it doesn't really matter. If I use this one, I'm going to take -3 times the top row here and add it to the middle row of that original null space matrix. So when I take -3 times -1, I get 3. I add that to -4. Well, actually, you know what? We can stop. Because I know, I mean, I don't actually need to do this, right? Because, let's see, -3, yeah.
You have to keep that first row.
Wait. Okay, so I multiply by I'm multiplying this row by -3 and adding it to this one. Did I make a mistake?
I think that
Did I mess this up? Let's do this again. Actually, you know what I'm going to do? I'm going to just use this. Let's just take 2 times the bottom row and add it to the top row. I'm going to get 0, -1, and -3. Okay. Right? And then I'm going to take 3 times the bottom row and add it to the middle row, and I'm going to get that. Did you guys notice how I made a mistake in my EROs, but I caught myself? And how did I catch myself? I caught myself because I wasn't getting a row to cross off before, right? That has to happen, right? If you row reduce this and you don't get any free variables, it means you haven't been able to come up with an eigenvector. And if you can't come up with an eigenvector, that's a problem, right? So this is the trick. You can catch yourself on those kind of things. Okay, so let's see if we can just write down a vector here. From the middle line, I can do that little trick just with the y and z. I can ignore x, and just with the y and the z variables, I can switch their positions and change the sign of one of them. So I'm going to put y equal to 3, and c equal to -1 right here. And then from the top row, I see that x and y have to be the same. So this will be a 3 right here. Okay? So this would be another eigenvector corresponding to lambda equals 2. Is everybody with me? All right, so then we can write down what S is and what D is. Can somebody remind me, how do we write down the matrix S?
Your eigenvectors.
Okay, we take our eigenvectors and we lay them into the columns of the matrix, right? So the first eigenvector there, it does not matter what order you put your eigenvectors into this matrix. However, whatever order I pick, when I go over here and write down the diagonal matrix, what are the features of this matrix here?
The eigenvalues corresponding to
Right, the eigenvalues that correspond to the columns that you built out of your eigenvectors go down those diagonals. So in this case, it's going to be like that. Now the person next to you might have put these columns in a different order, which is okay as long as they also shuffled the eigenvalues in the same manner. Okay, so that's it. Do you have to find S inverse? I had to read the question very carefully. It says find S and D. We've already done that. It doesn't ask us to do anything else. Find S and D. Yeah, there's this whole business about S inverse AS equals D, but you don't actually have to find S inverse right here. It's totally not asked for. Okay, so yeah, so that's it. That's pretty much it. Okay. Does that make sense so far? Okay, great. All right, so that's a good little computational example. Of course, what would be natural for me to do is have this as part A of whatever problem I'm going to ask, and then I would have a part B where I say solve x prime equals ax, right? So in other words, you know, a follow-up would be using that same matrix, find the solution. This was not on the quiz that I gave, but it would certainly be a reasonable thing now for us to do. Find the solution. And the thing is, we already know how to do this. This is a non-defective matrix, so we don't need to use the W's. There's no complex numbers, so we're not going to have to do anything with Floyd, right? It's going to be relatively easy. In fact, we can just write down the answer directly, right? C1 e to the t times 110, right? And then plus C2 e to the t times 101. Now, even though the same eigenvalue repeated twice here, you don't need to stack, and we never in chapter 9 simply stack t's the way you do in chapter 8 when you're stacking those x's. So there's no need to do that here because these vectors are already linearly independent without even having to do that stacking process, right? So you can just write it like that, and then the third term, C3 e to the 2t times 3, negative 1. And so this would be the answer, and you could literally just write that down in like 30 seconds after you've done all this other work. Question, yes?
And then if you had like an initial condition,
Yes.
just go from there as well.
Right. If we had an initial condition, then what you'd be using that for would be to solve for C1, C2, and C3. So you'd probably be plugging in C equals 0, which would just get rid of all the exponentials, right? And then you would just have an equation with 3 unknowns and 3 equations, basically. Yeah, Eric?
So then, if one didn't pull its weight, would we have to do the whole W1?
Yeah,
Okay.
yeah, you would. So if this was a defective matrix, you would have come over here, you would have figured out that the lambdas didn't pull their weight. So now over here, when I ask you the follow-up, you're going to have to do the W's. Yeah, which is stuff we just learned that you guys just turned in the homework on most recently. Yeah.
So just checking the W, well, like W2 for group 2, the W The one like right before the 0, basically.
Yes.
That one's always a multiple or the same as an eigenvector?
Okay, it's always an eigenvector.
Not a multiple of
Okay,
one?
so here's the deal. Okay, very good question. Very good question, and you caught it yesterday in my office, because there was one homework problem on the assignment that you guys turned in yesterday that was a little interesting. So, when you are doing the W's, in fact, we're gonna do an example of this in a second. When you do the W's, let's just take this case right here. The last W before you get to 0 is always an eigenvector. Now, if you previously had already calculated your eigenvectors, let's say that you found your, let's say it was a 3 by 3 and this was your eigenvector. If it was only one eigenvector, right, then your eigenspace consists of precisely just multiples of this one.
Right.
And so then, of course, this W2, as a quick check to make sure you did it right, this W2 should be a multiple of this one. And that is going to be true in the super defective case, because in the super defective case, you only get one eigenvector. Right? It's also going to be true in the mixed eigenvalue case, because in that case, you'll only get one eigenvector corresponding to the repeat eigenvalue. Right? But there's a third case, and it's the case that I didn't do an example of in class, which is the regular defective case, where you might actually have the same lambda 3 times, but get 2 eigenvectors here.
Mm-hmm.
In that case, all that you'll be able to tell me about W2 is that it is in the span of these two. It's not necessarily a multiple of this one or a multiple of this one, but it has to be some combination of these two.
Okay, cool.
Yeah.
Yeah, because I was checking my homework.
There's one problem where in the reg. So all 3 of these cases, the regular defective, the super defective, and the mixed eigenvalue, they all have slightly different phenomenon that goes on. The thing about the regular defective, actually, this to me, the regular defective is the easiest of the 3. The only thing is you just have to understand that the W2 is not necessarily going to look like a multiple of one or the other of these, because you have a whole 2-dimensional eigenspace, which is the span of these two. So your W2 could be potentially any combination of those two, right? And so that does come up once in a while. Okay, let's actually, now I'm gonna, that's it for the quiz. The quiz problems. Let me actually go to the review packet, okay? And let's try, in fact, I'm not gonna do these in order. I'm gonna try and do the 2 sort of longest ones first. Let's do number 4. So now I'm moving into the review, the actual thing that's online that I have typed up the answers to and everything else. Okay, so here it is, solve x prime equals ax, where A is equal to the following matrix, -2, -1, -4, I'm sorry, -2, -1, +4, and then we have 0, -1, and 0, and then -1, -3, 2, and this is actually an initial value problem. So let's suppose that x of 0 is the vector -2, 1, 1. Okay, so we have something, let's say that's the setup. Okay? Alright, so you guys help me out here. What's the first step?
Find our eigenvectors, eigenvalues and eigenvectors.
Find the eigenvalues and eigenvectors. So that means we have to look at the determinant of the matrix that we get when we subtract lambda off of the main diagonal. I'm going to just write it all out right here. Okay, so there is the matrix. And how would you recommend that I evaluate that determinant?
Do the cofactor expansion along the middle row.
Exactly, the middle row is going to be the winner here, right? We have a lot of zeros there. So let's expand the middle row. So there's, sort of a -0 there, and then plus -1 minus lambda times the 2 by 2 matrix that I get when I cross off the middle row and the middle column, and that's going to be negative 2 minus lambda times 2 minus lambda, and then plus 4, and then there'll be another minus 0 on the end of that. So I'm expanding that row. Do I want to multiply this all the way out? If you multiply it all the way out, you're going to create a cubic equation for yourself. Sometimes there's no way around that, but in this case, we already have negative 1 minus lambda factored out, and so I would recommend that we leave that on the outside. Inside of the brackets, I'm going to have a lambda squared, and then I have plus 2 lambda, minus 2 lambda, which actually cancels, and then I actually have a minus 4 and a plus 4, which also cancels. So it becomes a very simple factored form, like so. All right, so what are my lambda values? Negative 1 and 0 and 0. And it's always a good idea to check it with the fun facts again. So if we add up the main diagonal of the matrix, we get negative 1. If we add up these three numbers, we get negative 1. So it seems to work. And you could also check the determinant is 0, and it's going to work as well. By the way, if 0 is an eigenvalue of your matrix, do you remember what that means about your matrix?
It's not invertible.
That it's not invertible, exactly, because, well, the determinant of your matrix, from fun fact number 2, right? If you multiply all of your eigenvalues out, you get the determinant. So if 0 is one of your lambdas, it just means that your matrix is not invertible. Okay, so not that that's particularly relevant to the theory of chapter 9, but it's just good to make those kind of connections between things that we've learned in the past. Okay, so which eigenvalue do you want me to start with here?
Lambda 0.
Okay, we can start with lambda equal to 0. Let's do that one. Lambda equals 0. So I'm going to do the null space of, actually in this case, it's just the matrix itself that we started with. Negative 2, negative 1, 4, 0, negative 1, 0, and negative 1, negative 3, 2. So the thing of it is, guys, I know that I have to be able to cross off a row. If I cross off, for example, it doesn't really matter. I'll cross off the first row. If I cross off that row, I'm pretty confident that that's okay thing to do because the other 2 rows are not multiples of each other. So I've done something that's, I know that all 3 rows together are LD, but just the second and third row are LI. So I've removed that linear dependency by crossing off that row. What does this so in terms of the X, Y, and Z, what does this middle row tell you about X, Y, or Z?
That's y is 0.
That's right, Y has to be 0 because negative 1 times Y adds up to 0. Okay, so Y is 0. So if I go to the bottom line now, the equation here on the bottom that we are also working with is just that one right there in the box. If Y is equal to 0, well then we have X equals 2Z. So if I just let Z equal T as my free variable, then I can solve for X and I'm going to get 2T. Okay? Busting out my variable, this is going to give me an eigenvector 2, 0, 1. Does this matrix, does this eigenvalue pull its weight? It has a weight of 2, but it only gave me 1 eigenvector, so this is defective, right? We can write down 1 solution, but we won't get 2 solutions yet, right? So the first solution, remember how it works? It's e to the lambda t times b. This is one of the most important things in chapter 9 to make sure you know how to do. Lambda is just 0 right now. So if I just get rid of the lambda, then x1 of t is just that vector over there, which is just 2, 0, 1. So there's your first solution. It's just a constant solution. Okay. So we're going to need to do the W business to get a second solution. So remember that the formula in this defective, so this is the mixed eigenvalue defective case, right? To get the second solution, we're going to have something of the form e to the lambda t times the quantity w1 plus t times w2. So this is a good chance to practice this defective scenario. So remember how it works again. We're going to choose w1 so that it survives the first power of a minus lambda I, which is just a, by the way. Right, a minus lambda I, right there. But that w1 does not survive a second power of a minus lambda I. Okay? To figure this all out, I'm going to need to know what a minus lambda I squared is. So I almost always just do that first. Okay? So in this case, a minus lambda I, when I square it, well, it's just a squared because the lambda was 0. So all I'm going to be doing here is taking this matrix times itself, right? It's just multiplying the matrix times itself. And I'm wondering if you guys would be kind enough to let me just tell you what it gives you. Let me just do that. So when you square this matrix, and by the way, you're squaring it before you did any EROs to it. Okay, so you literally just as is. When you multiply it by itself, and make sure that you know how to do that, because I get very sad when people in week 15 are not multiplying matrices correctly. So make sure you know how to multiply matrices out. You're going to get 0, negative 9, 0, and then 0, 1, 0, and then 0, negative 2, 0. Something like that. Okay, so we are looking to choose a vector for w1 that will survive this matrix, but will not survive this matrix, right? Can somebody give me a proposal?
1, 0, 1. Or just 1, 0, 0.
Let's just make it as easy as we possibly can. How about 1, 0, and 0, okay? The reason that that works out so nicely is that, well, then W2 becomes just simply the first column of the matrix A right here, yeah? So W2 becomes, in other words, you take the matrix A minus lambda I, I'll just remind you here, you just take A minus lambda I and multiply it by W1, and in this case, you're just going to pick off the first column of the matrix A minus lambda I, which is just A, and there it is. Always a good thing to check, is this actually an eigenvector? Because it's supposed to be. And I can see that, yep, it is in fact a multiple of the eigenvector that we had found earlier. So it's still an eigenvector. Okay? All right, great. So that means that I can write down my x2 now. I think I'll just do it right up here. x2 of t would be, e to the 0 times w1, which was 1, 0, 0, plus t times w2, which is negative 2, 0, negative 1. Perfectly fine to leave it like that. Some people I've noticed, they kind of like to put it all together. If you look in the, sometimes in the back of the book, they try to take up a little bit less room to express the answer. And it would just look like this, okay? So this is your second solution. So far, so good? Yeah, Tessa?
Just checking, so when we're creating our W's, when there's a 2 by 2 matrix, we know it's going to become all zeros, so we don't have to be particular.
You won't be worrying about it, yeah.
And then, so the times we do have to multiply is when it's this mixed case, or when it's the first.
Actually, it's pretty much just in the mixed case.
Because.
Now, there was a problem on the homework that was a little tricky. The homework that you guys did yesterday, where the A minus lambda I squared matrix, I think was something like this: 1, 2, 1, 1, 2, 1, 1, 2, 1. It did not generate a lot of zeros. So you're looking for I forget what the original matrix, what the A minus lambda I was, but this was the square of the matrix. So you were trying to choose a W1 that would survive whatever that original matrix was, but wouldn't survive this one. And unfortunately, 1, 0, 0 does survive this matrix. And so does 0, 1, 0, and so does 0, 0, 1. You had to be a little more particular for this problem to choose your W1 carefully. So for something like this, you can actually row reduce this and solve it if you want to, just like you did in chapter 2, right? You're gonna cross off of these 2 rows and okay, solve it by back substitution. Or you can just kind of eyeball it. You say, well, I could use that vector, right? -2, 1, 0. If I put that right here, -2, 1, 0, and if I multiply that out, everything is going to get zeroed out. Or you could have chosen -1, 0, 1. That would have also worked. Because now, if you do that, okay, again, just check it out. -1 plus nothing plus 1, that's 0. -1 plus nothing plus 1, that's 0. -1 plus nothing plus 1, that's 0. Right? So there's multiple things you can choose. I feel like so much of the time we just end up choosing 1, 0, 0. It's important to realize that there are cases where that doesn't work. It won't work basically if this first column isn't all zeros. Here, first column is all zeros, so yep, we just choose W1 to be 1, 0, 0, and we're good to go.
Okay, so for that special case, but then also if we're in a super defective case and we're finding W1 and W3 for a 3x3 matrix, we also need to multiply it out because it doesn't become until the 3rd iteration that actually all zeros.
Right,
Okay.
right, that's true. But you will get the all zero matrix eventually.
Right,
In that super defective case. The super defective case is annoying because you got to do the W3, W4, and W5. But one thing about that case that's nice is that at least for a 3x3 matrix, the cube of A minus lambda I will always have to be the zero matrix. I didn't really ever prove that, but that is a fact. Okay. Yeah.
No, I
Ryan?
was just having you repeat. If for some reason you can't pick, you
1,
could
0,
just
0. Yeah.
augment it with the 0
Mhm.
and then solve for that.
Yeah, just solve it by
And
back
then
substitution.
bust out the variables, and that'll be your.
Yeah, that's right, exactly right.
And then to figure out your W2, you have to like actually multiply.
Well, once you've chosen your W1, right, the easiest way to get W2 is to just multiply W1 onto the matrix.
Right.
Yeah, exactly. So now this would be A minus lambda I, the original. See, I don't try to memorize like, well, which matrix do I multiply by which vector? I just draw the picture and say, oh, I have W1 already figured out. How am I going to get W2? This picture reminds you how to get that. Again, this is not in the textbook, but it's a really handy visual way to, I think, for me at least, to remember it. Okay, oh, we're not done. We have to find the other eigenspace, which is lambda equals -1. And we also have an initial condition. We have a little more work to do. These problems take a while. I'm doing the long ones first, and then the faster stuff we'll do later. So lambda equals -1. I tell you what, because we practiced this already a little bit, are you guys comfortable if I just tell you what you're going to get for that? Let me just do that. So turns out that you're going to get the eigenvector that corresponds to that is 9, -1, 2. So you can check that or work it out for yourself. And so we get a third solution, x3 of t, which would be e to the -t times 9, -1, 2. Okay. This is x3. And if I was doing a little better here, I would have put a box around this as well, just so it's easy to find stuff. Okay. So we now have everything we need to write down the general solution to this system. So the general solution is going to be, you guys know how to write it down? At this point, we're just having to report everything that we figured out. So C1 times the first solution, which was 201, right? Plus C2 times the second solution. I'll write the, just to save space, I'll also write the compact form of it. 1 minus 2t, 0, and -t. And then plus C3, e to the -t times 9, -1, 2. This would be my general solution to my system. Okay. So am I done?
You gotta do
times 0, the vector result should be -2, 1, 1. So let's just practice that one time. So if I plug in 0 for t, well, it's just c1 times 2, 0, 1 plus c2 times, again, I'm putting in 0 for t, so it would be 1, 0, 0, plus c3 times e to the 0, which is 1, times the vector 9, -1, 2, and all of that is equal to whatever was given to us, and what was given to us was the initial condition -2, 1, and 1. Okay. Well, now, what we need to do next is realize that looks like just one equation, but it's really 3 equations. We have 3 unknowns, don't we? C1, C2, C3, and that vector equation will give us 3 equations that we can work with. If we go across the top of this vector equation, right, we'll get 2c1 plus c2 plus 9c3 equals -2. If we go across the middle, we'll get -c3 equals 1. And if we go across the bottom, we'll get c1 plus 2c3 equals 1. Okay? And you can put this into a matrix and solve it, or in this case, I'm going to go a little faster and just figure it out kind of step by step. The middle equation tells me that c3 is -1, right? And then once I know that, I can put it right here. If I put in -1 right here and then I move that term to the other side, I can get c1, which I guess would be equal to 3. So c1 is equal to 3, and c3 is equal to -1, so I have 6. So up here I have 6 plus c2 minus 9 equals -2. And so I think c2 would have to equal 1. I actually prefer usually when I see you guys putting them into a matrix, because that's kind of what we've been learning here. But in this case, it's certainly not wrong to just kind of figure it out in your head almost. That would be the specific constants for this initial value problem. Okay? So c1 is equal to 3. So we're solving these 3 equations right here. c1 is equal to 3, c2 is equal to 1, and c3 is equal to -1. Look okay? So then my final answer, finally, is to actually just plug those numbers into the general solution that we had right here. This was the general solution, right? So now I can just put in c1 equals to 3, so it's going to be 3 times 201, right? And then plus 1 times 1 minus 2t, 0, and -t. And then the third term has a minus e to the -t on it, times 9, -1, and 2. So whenever you have an initial value, you're actually going to solve, you're going to be able to figure out the constants that are in the general solution. Okay, any questions on that one? Does that make sense? Okay, these take a little bit of time, but you know, it's not terribly difficult. It's just a little bit of a time crunch to figure it all out. All right, let's do another one. I'm going to go backwards and do number 3 from the review packet. So number 3 and number 4, these are the 2 longest ones. This one says solve x prime equals ax, and I'm going to give you the matrix A right here. It's going to be the matrix -1, -4, excuse me, -2, and then -4, -5, -6, and then 4, 8, and 7. Excuse me. And there is a hint here that one of the lambdas, one eigenvalue is, so I'm going to give you one of them. I'm going to give you 1 plus 2i. That's one of the lambdas. Okay, so we're going to start this problem. I'm going to come over here. Can I erase on this side? Everybody got this down? Go ahead and get rid of this problem. Let's do problem number 3 over here. What's the first step when you're solving one of these? Find the lambdas.
Are your characteristic equation?
So the characteristic equation is normally how you find the lambdas. In this case, it's going to be pretty nasty, right? Because there's no zeros in it. So can we get the lambdas without working through the characteristic equation approach?
Yeah.
Fun fact.
Yeah.
The fun facts, right? Because if this is an eigenvalue, what would be another eigenvalue?
The
Like
negative.
conjugate of this one, right? So there's also lambda bar, is usually the way they write it, which is 1 minus 2i. Now you've got 2 of the 3 lambdas, because these always have to come as a pair, right? And how much does that add up to so far? 2. So then I look at the matrix, and the main diagonal, the trace, is -1 plus -5 plus 7, which is 1. So all 3 lambdas have to add up to 1.
Got a negative 1?
So, right, so the first 2 add up to 2, so that means that the third lambda, I guess I'll call it lambda 3, would be -1. Is that what we said? Yeah, so there we go. All right. So, by the way, is this matrix defective or not, or do we not know yet?
It's not.
It's definitely not defective because why?
They're all like
Like
this.
this.
Right, there's no repeat lambdas. These are not the same, right? So we have 3 distinct lambdas. So it's non-defective, which means I don't have to do the w's here. But I do have complex numbers to fight with. So where do you guys want to start? Do you want to, I don't really care, do you want to start with the complex number pair, or do you want to start with -1 first?
I like starting with the easy.
I was gonna say, let's get negative 1 out.
Get that out of the way. Okay, so we can do that. That's fine. Let's do lambda equals -1 first. So I'm going to take the null space of the matrix that I get by adding 1 to the main diagonal. So if I add 1 to the main diagonal of the original given matrix, I'm going to get something that's looking like this. Adding 1, so 4, 8, and 8, something like that. Okay, so this is what we have so far. Okay, it's a little bit of a mess. We have to do some EROs. I think the best thing to do here is actually to put the bottom row on the top, but divide it through by 4 first. So I'll just put 1, 2, 2 up on the top. And then the top row, I'm sorry. Let's just take the bottom row and add it to the middle row. So that'll put a 0 there, it'll put a 4 there, and it'll put a 2 there. And then as we know, we have to go and cross off a row, so I won't bother to write down the third row, because I know that I've got a nice pivot structure right here.
So,
I mean, the third row would have been, I would have had to write down the top row because I haven't touched it yet. But 0, -4, -2 is just a multiple of 0, 4, 2. So do you see what I did to get this middle row here? What I did is I added row 3 to row 2.
and then, you just got rid of the top row.
And then I just said, all right, I don't need to bother with the other row. You're always going to be able to get rid of one of the 2 rows, or one of the 3 rows, I should say. Making sense? Now what I would do with this is I would just do my little switch trick on the YZ component, switch the 4 and the 2, but I'm also going to cut them down by a factor of 2, just to make smaller numbers. So instead of 4 and 2, I want you to imagine that this is 2 and 1. Right? 2 and 1. If that's a 2 and a 1, then I can switch their positions and change the sign of one of them, and I would get something like -1 and 2. Okay. And then I can go back up to the top equation, x plus 2y plus 2z, supposed to add up to 0. And if I put in -1 for y, and if I put in 2 for z, I'll get an equation that I can quickly solve for x. It looks like it's going to be -2. Okay, so there's your eigenvector corresponding to -1. So we can write down the first solution here. x1 of t is e to the -t times the vector -2, -1, and 2. Okay, so just put that down like that. And now we've got that part out of the way. So far so good? Let me know if I'm going too fast. You know, I'm really not in a rush, so we can take all the time we need to clarify stuff. But what you have to realize is that while we're doing these kind of problems, these last couple of examples, we're actually reviewing chapter 7 and chapter 9. Right? We've seen a lot of both of those, and that's like half the midterm. Right? So this is good to be doing some of this stuff. Okay, let's go on to the complex numbers that we came up with. Let's take I would always recommend taking the positive lambda value, because then when you use the Euler identity, you don't have to think about a minus sign. It's just easier with a plus sign, I think. Okay, so this is the lambda, and so let's figure out what the null space is that we have to study. Okay, so we're going to subtract 1 plus 2i from the main diagonal of that matrix. So we're going to get negative 2 minus 2i, negative 4, negative 2, and then we're going to get negative 4, and then negative 6 minus 2i, and then negative 6, and then on the bottom we've got 4 and 8, and we take 7, we subtract 1 plus 2i, so that's going to be 6 minus 2i. Okay. Whew. That looks rough. But amazingly enough, it's not so bad. I see one glimmer of hope with this matrix to make my life a little easier. And that is that if I add rows 2 and 3, I'll create a 0 in the first position. But by the way, remember, you're going to get to cross off a row just because you know that you can, right? Anytime you're doing one of these eigenspaces and you have to do a corresponding null space, you're going to get to cross off a row. But I'm not going to do it quite yet. I'm going to leave the first row the way I found it. Okay? It looks bad, but it's not as bad as you think. I'm going to go ahead and add the, I guess I can just add the bottom row to the middle row. I'm going to add the bottom row to the middle row to make a 0 there. When I do it in the middle position, I'll get 2 minus 2i. And when I do it at in the last position, I'll get negative 2i. And guys, these two rows are not multiples of each other anymore. So I'm going to now imagine crossing off the third one. You see how fast that actually was? So it was a little bit lucky. It was lucky that we could just get a 0 in that first row so easily, but that's exactly right. I mean, to be honest with you, if you wanted, you could have just crossed off this row to begin with and said, look, these two rows are now multiples of each other, so there you go. But then you don't have it row reduced yet. I prefer this. Why do I prefer this? Oh, well, because I can write down my vector pretty easily. Right? How do we write it down? I can do my little switch trick right here. Yeah?
Yeah.
Just with the y and the z, so I'm going to take the negative 2i and change it to positive 2i and put it in the middle. And I'm going to take what was in the middle and leave it alone, but put it in the bottom position. And you can divide that through by 2 if you want to, but I'll do that later. So what I did is, just with these two numbers, so this just goes right there, this just goes right there, and then I have to change this from a minus to a plus. It's that whole thing that you've seen me do so many times when I only have two unknowns. I didn't let you do it back in chapter 2 because I wanted everybody to get used to the being able to do the actual process of doing EROs, but now we find that this is a fast thing that we can get away with. They're really good with the y and the z part. Now, that top row is where we're going to figure out what x is. So what is this top row equation? Well, if you think about it, it just says that negative 2 minus 2i times x minus 4 times whatever we said y was. I said that y was 2i. Minus 2 times whatever we said z was, which was 2 minus 2i. All of that has to add up to 0. And it, again, maybe doesn't look that easy, but let's just see here what's going to happen. So this is negative 2 minus 2i times x minus 8i minus 4 plus 4i adds up to 0. And so that's negative 2 minus 2i times x. Let's just move everything to the other side of the equation here. We're going to get 4 plus 4i. I think if I move everything to the right side, the minus 4 becomes a positive 4, and the negative 8i plus 4i is a negative 4i, but I'm moving it to the other side of the equal sign. And actually, that tells me, if you think about it, that tells me that x equals negative 2. Because if you just multiply this negative 2 minus 2i by negative 2, you get 4 plus 4i. So, right in here, negative 2. Now, if you want to, you can cut this vector down by a factor of 2. Because any multiple of an eigenvector will also be an eigenvector. Or we can just leave it. It really doesn't matter how we handle that. I'm just going to leave it. Why not? No need to get too fancy with it. But what we're going to get now, guys, is I'm going to write it as, I don't think I've ever written it like this before, but I'm going to be putting my second and third solutions together. I'm going to be building both of them from this one expression. So I'm going to call it x23. That's not a 23, that's a 2 and a 3. Okay, so I'm just going to write it this way, and we just take e to the lambda, which is 1 plus 2i times t, times the eigenvector, which is negative 2, and then 2i, and then 2 minus 2i. This is the very compact way of writing it. But as you know, that's not an acceptable answer because it has i's everywhere throughout. So this is where we have to expand it a little bit. So the way I like to do that, I take out the e to the 1 times t. And then I use the Euler formula on the e to the 2it. It just gives me the cosine of 2t plus I times the sine of 2t. And then I take this vector and I also break it up into a real and imaginary part. So there's a negative 2 here, right? There's no real part in the middle, so that's going to be a 0 right now. On the bottom I have a 2. Okay? And then plus I times, I have to figure out where are the I parts of this vector, right? There's no I in the first slot. I is multiplied by 2 in the second slot, and it's multiplied by negative 2 in the third slot. Okay, so there you go. That's what we have. And now I'm going to come back over here. I don't think we need most of this anymore. I just need to keep the x1 on the board. Let's see if we can figure out how to get 2 real solutions from this. Do you guys remember what we do? I call it FLOY, right? I do the FLOY thing. I FOIL this out, but I'm going to group them in a strategic way to combine things in a way that we can get rid of the complex numbers. So what I'm going to do is for the x2 of t, right? What I'm going to do is I'm going to combine the first and the last only. So what will that give me? Well, it's e to the t times, so the first term here, right, would be what? Cosine of 2t times negative 2, 0, 2. So let's put that down. Cosine of 2t times negative 2, 0, 2. That's the first part of the FOIL, right? And then the last part is going to be over here, right? Sine of 2t and 0, 2, negative 2, but with I squared in front of it. I squared, of course, is negative 1, so I just have a minus here. Right? So it would be minus the sine of 2t times the vector 0, 2, negative 2. So there, my friends, is your x2 of t. Okay? And then finally, the x3 of t is going to come from combining the outers and inners of this FLOY. So you see the flow here, okay? So we have e to the t again. The outer part is cosine of 2t times 0 to negative 2. So cosine of 2t times 0 to negative 2. And then the inner term would be plus the sine of 2t times negative 2, 0, and 2. And if you guys are willing to help me out and put boxes around what you've written as you go along, so we've got a box around x1, we've got a box around x2 and x3, your final answer is just, well, it's the general solution. And I don't need you to like write the whole thing out again. You can just write x of t equals, but make sure you do write this, because this is part of the solution. C1 times x1 of t plus C2 times x2 of t plus C3 times x3 of t. And as long as I can find x1, x2, and x3 in your previous work above, I'm willing to accept that. Usually if I'm in a pretty good mood, I don't take off points when people don't put arrows on their vectors, but I really don't like that because these are vectors. So try to do that, because I could occasionally be in a bad mood and happen to take off. I wouldn't take off much, but I mean, I do get frustrated sometimes if people aren't putting arrows on things, because the notation is always so confusing, and doing ourselves a favor and distinguishing vectors from scalars is a good thing. So these are x1, x2, x3 with arrows on top of them. Does this make sense? Okay, so there you go. That's a couple of problems, problems 3 and 4 in the review packet that have a lot to do with solving the systems in chapter 9. And I love doing the chapter 9 problems. Oh, you're still copying something. Sorry.
I don't want to break something.
If you can't get to it, what will happen is you'll go back to the video and skip an hour and 15 minutes into it, and you'll find the problem there. Okay. All right. What am I going to do next? Why don't we do? We're going to have to do some stuff about. Let's do some 2 or 3 theoretical type questions, and that'll segue into maybe some stuff on kernel and range as well, which I think would be good for us to go over. So I'm going to go straight to problem number 1 on the review sheet here. So number 1, it says, suppose A is a square matrix with a cubed minus 2a squared plus 4a plus 5i equals 0. And then let lambda be an eigenvalue of a. Can I erase that, Brian?
Yes.
Oh, perfect.
Thank you.
No problem. Okay, so there's the setup. We've got a square matrix with a certain equation. Suppose we have an eigenvalue of that matrix. For the math majors, this is an incredibly important theorem that we're going to be demonstrating. It's called the Cayley-Hamilton theorem, which says that anytime you have an equation that your matrix satisfies, then so does any eigenvalue. So show that lambda cubed minus 2 lambda squared plus 4 lambda plus 5 is equal to 0. So this is a famous result. And it would be true for any polynomial. There's nothing special about cubic or about what the coefficients are. I just basically made all of that up. Any numbers I want, I could use there. Okay? So this is something that in an upper division linear algebra course, they may even try to prove this one for you. We're just going to prove it for a specific case just to get the feeling of how it works. But it is always true, actually. Okay? So I am, this is a theoretical example because there's no specific matrix in mind here. It's kind of abstract, right? A little bit abstract. And so I am wondering if anybody, I wonder if my blue marker shows up on the on the video here. Wondering if anybody has an idea what to start off with. Yeah, Brandon?
If we can substitute the A's for their the diagonal equation, SDS, or S inverse DS.
Okay, wait a minute. Is this a diagonalizable matrix?
Ooh, we don't know.
Oh.
We are not told that. Yeah, so we can't really assume that. I mean, that's the only problem with that. Otherwise, yeah, you could always feed in the diagonalization equation. Yeah.
What about using the fact that like A times V, the vector V equals the eigenvalue times V?
That's it. That's it. Did everybody catch that? The most important equation in chapter 7, especially if you're talking about a theoretical problem in chapter 7, right? If you guys just simply write this down, AV equals lambda V, you're going to get a couple of points just for that, right? So just memorize that thing, right? Just make sure you know it because it's probably going to be useful, okay? So this is kind of given, right? This is given, and I just want to mention here that V, now the V is not part of the question. We are bringing the V into the solution right now, so we should explain what it is. If you're going to bring something new into your solution that's not appearing over here, then it's a good idea to tell me what it is. So V is an eigenvector. And I'm just going to give you a quick little hint that this will be useful later, is to remember, I don't talk about it very often, but it's important. It's part of the definition of an eigenvector, which is that it cannot be zero. And we're actually going to need that in this problem to finish this problem, okay? So this is our starting point, AV equals lambda V. Now, this is a vector, and this is a vector. So we have to be really careful. Would it be helpful? Okay. I'm going to tell you some things that people do, all of which are not valid. One thing that people do with this is they decide to cancel the V. Okay. Do not do that, because now you're saying that this matrix is equal to this number, and the red pen is going to be coming out pretty fast on that, right? So you cannot have a matrix equal to a number. That's one thing. Another thing that people do that is completely illegal is they say, well, I see a squared and a cubed over here, so I'm going to square both sides. Okay? And the red pen is going to come out just as fast on that as well, because you cannot square a vector. I can square a number, right? We don't want to do that. I can even square this matrix. Like if you wrote down a squared, that would be okay. But AV squared is totally not anything that makes sense. So we've got to erase this before anybody sees it. Okay, so do not cancel vectors. Do not square both sides of a vector equation, because both of those things get you into trouble. So now that I've told you what you can't do, does anybody know what you can do?
Subtract.
I could subtract. It's not what I'm going to do, but I could do that.
Multiply, like right multiply both sides by vector V.
So can I do this? AV times V?
Well,
Is that what you mean? Equals lambda V times V?
yes.
Okay, this is multiplying two vectors.
Not with that, but with.
Oh, with this equation. Oh, okay. Yeah. Okay, so this is a matrix equation, and we can apply it to a vector on both sides. That is true. So we can certainly do that. Can we do that in a couple minutes? It's exactly what we want to do, but I want to set us up for that to be helpful to us. So Solomon's got the right idea. We're going to apply this equation to the vector V in a minute. But is there something else that we maybe need to do? Oh, the heck with with it. I'm just going to do that. I like your idea, and it'll help us to see where we're going to go with this. So what Solomon is saying is he just wants to take the matrix equation. This is perfectly legal. Take the matrix equation and apply it to V, right? And that's equal to 0 applied to V. I don't have a problem with that, because you can take a matrix, right? We all know that we can do this, right? You can take a matrix and multiply it by a vector. So there's nothing wrong with that. But what do you get when you take the 0 matrix and multiply it by any vector? The 0 vector, exactly. So we have the 0 vector over here. Now, what can I do on the left side?
You can just distribute.
I can multiply it out. I can distribute it out, exactly. So what would that look like? Well, it would be a cubed v minus 2a squared v plus 4av plus 5v, right? Yes?
So since it's all equal to the 0 vector, and
Yes.
technically, are we saying that the left side should become synonymous with A by V?
No.
Okay.
No.
Okay.
And the other thing is, okay, let me get rid of this again. I'll write it back down in a second. I have something times something equal to 0. It does not mean that this is 0 or this is 0, though. Actually, we already know that this part is 0. That's not really the point, though, right? So we're not trying to just say that this is 0, that this matrix is 0, because we already know that that's true. We need to just FOIL this out, which is what I had up here a minute ago. A squared v plus 4av plus 5iv is just v. Okay, so I can just get away with that. But what I'm wondering is, okay, so I can see right here, for example, this av is just lambda v. It's given. But now I realize, oh, I would like to know what a squared v is and what a cubed v is. Can we get those things? So again, if I start from this one, a lot of people like to try to square both sides. That's not what you want to do. What you actually want to do with this is just apply A again on the left of both sides. And be sure it's on the left, guys. Something like this makes no sense. Because here, think about it, you're multiplying an n by 1 column by an n by n matrix. The sizes don't even work. So keep the matrices on the left, right? So put an extra a on the left here and here. And now this becomes lambda av because I can switch the lambda with the a because lambda is just a number. And that just gives me lambda squared v because the av is lambda v. So look at that. A squared v is equal to lambda squared v. All right, let me summarize that over here.
So
See where we're going?
you can square it.
We're not squaring anything, we're multiplying by itself.
Right.
It's just like an extra step.
Right, just to do it correctly.
Yeah.
Right. So from AV equals lambda v, we get a squared v equals lambda squared v. That is legal, and it's probably maybe what you would think of doing. And I bet you know what else I would want to do right now? The cube, exactly. So I won't show all of that out, but that's just going to be a cubed v equals lambda cubed v. Okay, with me?
Yes.
And so thus, we get, if I come right back to this is an equal sign here, sorry. If I come right back to this boxed equation, I have lambda cubed v minus 2 lambda squared v plus 4 lambda v plus 5v equals the 0 vector. And I'm, again, being careful with arrows on my vectors here. And now what can I do?
Take out the v.
Right, I can take out the v. Let's take it out on the right side because that's the side that it's on. Okay, so with this class, you almost never need to put the vector over on the left. Just keep it on the right, put the scalar out in front, and your scalar is just going to be exactly this big scalar right here. Now what do we have? We have a vector that is not 0, by the way.
Which means that all of the scalar has to be 0.
Right, you have this vector, you're scalar multiplying it by something and getting 0. And the vector that you started with is not 0. The only way that you can take a non-zero vector and multiply it by a scalar and get 0 is if that scalar was 0. So thus, lambda cubed minus 2 lambda squared plus 4 lambda plus 5 is definitely 0. Make sense? There's an example of this somewhere else where I can't remember where it is right now. Maybe it's in the group work or something, but these problems are a dime a dozen. Like, all I have to do, I can just change these numbers and just ask the same question again. Right? It doesn't matter what the actual polynomial is. That actually has very little to do with it. But the first thing is, here's some partial credit right here. Even better if you remind me that the vector is non-zero. And then the big thing is, what are you going to do with this? Do not cancel the v. Do not square both sides of it. The thing to do is just apply the matrix on the left of both sides. That is okay. And that's actually what you need to do. Okay? Great. All right, I like that problem. You guys like that problem?
No.
Not really? Because it's kind of like proofy. Yeah, maybe I should. All right, maybe I better practice another one then. I want you guys to be happier with this. Let's try another example. Okay, let's go to, which one is it? Well, it's actually number 2 on the handout, on the practice problems. So number 2 says, suppose lambda 1 and lambda 2 are different lambdas, and these are eigenvalues of A. With corresponding eigenvectors v1 and v2. Okay, so the usual thing, we have these eigenpairs, as we call them. Okay, and then what we're going to do here is we're going to show, and if this was actually one that I was going to put on the test, I'd probably give you a hint. So don't stress out too much on it. It kind of goes back to something from chapter 4, so I would feel bad to just throw this at you right now. But anyway, the question is going to be to show that those two vectors are Li. And this is, again, I'm not really going to be doing a lot of this kind of thing on the midterm because we're not really talking about, we are talking about linear independence in chapters 8 and 9 using the Wronskian, but that's completely different than what this question is about. So, but this is great review because we do have a final just around the corner as well, and this is a definition that I want people to know a little bit about. So let's think about this. So what it's saying is that if you calculate eigenvectors for different lambdas, that those eigenvectors will be Li. The only way you get into trouble with finding eigenspaces is when you have a repeat eigenvalue that does not pull its weight. This is sort of saying, well, as long as these are different lambdas, everything's going to be cool, right? The eigenvectors that go with those different lambdas will be Li. Okay? We've kind of been using this all along. I've just never really proven it or explicitly mentioned it. Okay, so let's see if we can work this out. Do you guys remember how to show, let's focus on this part first. Do you remember how to show linear independence? In other words, what's the format of it? Like, what do you start off with, and then what do you try to accomplish?
You assume the limit is 0.
Assume, and so there's a linear combination of the vectors, so that would look like what? C1 V1 plus C2 V2, and we assume that that adds up to what? The 0 vector, right? And then we will show that the constants C1 and C2 are both 0. This is the framework for any like abstract problem involving linear independence. Okay, so this is what we're going to start from. Now in this equation, I don't see the eigenvalues, I don't see the matrix, right? I just have just the eigenvectors themselves. That's all I've got so far. At some point, I'm going to need to use the fact that I have a couple of eigenpairs here. So what else could I, before we actually figure out how the whole problem is going to be solved, what else might I want to write down right now?
The fact that A, B, vector B equals.
Well, there is no vector v here. I have a v1 and a v2.
V1
A v1 equals
the eigenvalue lambda
lambda
1
1
V1.
v1. Excellent. Okay, because that's an eigenpair, right? Lambda. It says here these are corresponding, right? So lambda 1 goes with v1, and also what else can we write down?
Same thing with V2 and lambda 2.
Exactly. AV2 equals lambda 2 v2. So there you go. There's partial credit right there. Just write down that equation and we've got it. Okay? So I'd like to use these facts, but my box doesn't have the matrix or the eigenvalues in it. So is there some way that I can like bring the matrix or the eigenvalues into play here? Because the box is what we're really starting from.
You can multiply by A because that's the same in both equations.
Kind of like the last problem. We started out with, AV equals lambda v, and we applied the matrix to both sides of it. That's what we can do right here as well. So I'm going to multiply the box, I'm going to just write it like that, by A. And if I do that, I'll get A C1 V1 plus A C2 V2 equals A times 0. What is A times the 0 vector going to be? Just 0, right? Okay, great. So we've got that. We're just putting an A in front of everything. Perfectly good idea there. All right. Well, let's see what we can do now from there. Any suggestions what I might want to do?
Remove the constants out in front and then substitute in.
Yeah, the whole point of doing this was, the whole point of multiplying by A was so that we could get AV1 together and get AV2 together. So I need to get those constants out of the way, right? So then what I have, if I do that, is C1 times AV1 plus C2 AV2 is equal to 0, right? And now, as Tessa mentioned, we got our A1, B1 here, and our AV1 here, and AV2 here, and we can replace them now. So let's do that. So we have C1 lambda 1 V1 plus C2 lambda 2 V2 equals to 0. So I'm going to put that in a box because that seems like it's a pretty good step forward. Okay? Everybody with me so far? The structure is just start from this assumption. We're going to try to show that the constants are all 0. And we need to take advantage of the eigenvalue-eigenvector relationship, which is the AV equals lambda v, and we've done that by multiplying through by A. Okay. The very first time I saw this problem, I sort of got lost at this point. Like I didn't know what to do next. I'm still trying to show that my constants are all 0. But it seems a little tricky to get that right now. This is where I probably would put a hint, something, a little idea to help you out. Unless somebody wants to offer an idea. Does anybody see where we can go?
Can we try and assume that V1, V2 is a V?
That's gonna take us down a road that, I mean, that may work, but if we were gonna do a contradiction approach, we probably should have started at the beginning from that and kind of worked it from there. We're kind of already going down the train tracks here with this idea of showing that the vectors are Li. Does anybody have another idea? Yeah.
So we know that the eigenvalues are different.
Yeah, we haven't used that yet. We're gonna use that. But the problem is, I mean, the C1 and the C2 could kind of somehow make up for that. Like we don't know what C1 and C2 are yet. Well, the trick here, and this one is a little, don't worry about this, like this is too hard. I wouldn't be asking you to dream this up on your own. But you see, we actually can replace C2, V2 over there with negative C1, V1. We have this boxed equation, we can go back and use it, right? In other words, what I could do is I can take this equation and I can replace in fact, I can pull the lambda 2 out in front if I want. C2, V2 is just negative of C1, V1. So just go back and replace. That's the trick, and that's not maybe right on the tip of your tongue. So that turns out to be great, because now you see that I have a C1 in both terms. I have a V1 in both terms. And I have a lambda 1 minus a lambda 2. So this is going to end up getting us where we're trying to go. Because is V1 0?
No.
No, because it is a
Eigenvector.
eigenvector. So an eigenvector cannot be 0. Is lambda 1 minus lambda 2, can that be 0?
No, because they're not equal to each other.
They're distinct, right? So they're not equal to each other. But yet here you go, you have a scalar multiple of your vector that becomes 0. So somehow this scalar has to be 0. If the lambdas aren't 0, then C1 has to be 0, right? So thus C1 is 0, all right? And once you know that, you can kind of just come back to here, get rid of that term, and now you've got C2, V2 equaling 0, right? So hence, C2, V2 is 0. And V2 is not 0, right? Same old reasoning again, right? And so therefore, C2 is also 0. So we've got both of our constants canceling out. Make sense? This one's too hard for the exams. Certainly without a pretty good hint, it would be a little too much. But I don't mind in the review session showing it to you, because it has a lot of good ideas in it that you can be practicing. The eigenvalue eigenvector equation, remembering how you prove linear independence. I know that's not really for chapters 6 through 9, but it is going to be something to look at for the final. So I just thought it'd be a good time, as good a time as any to show it to you. Okay, anybody have any questions on that one? Need a little exposure to like a few theoretical problems. There's also some theoretical problems that you could look at that are in chapter 7.1. Just things like, okay, if you know, lambda is an eigenvalue that corresponds to V, and mu is an eigenvalue that corresponds to something else, right? And then you like combine them somehow. You can create, like maybe you add them together or something. Lambda plus mu is an eigenvalue for V plus W or whatever it was. I can't remember. But anyway, there's some problems like that you can kind of practice on a little bit to kind of get the idea. Okay, if everybody's good for you guys watching at home, we can always pause me and rewind me and watch this again. But I'm going to erase it for right now and go on to another problem. I should probably make sure my phone isn't dead. Could just be sitting back there. Make sure that it's still recording. I'm going to transition into some stuff on kernel and range. I'll check in a second, Brian. I'm just a little worried. Just don't want to. The last time I tried to check it, I almost bumped this thing and knocked it over, and it messed everything up. Hey, it's looking good. Okay, it's still recording. I don't know how big the file's going to be. I'm going to try to get it off of there and onto my computer. I want to transition into some kernel, range, one-to-one onto, all that stuff. And I'm going to start with a theoretical problem about it, which I think you may have even done in the homework. I can't quite remember. And then we'll try a couple more computational examples. So let's do this one here. Let's suppose that t, this is number 11 on the review packet. Suppose that t is one-to-one, is a one-to-one linear transformation. And, oh, this is perfect because this is also about linear independence, so we can kind of keep using what we were just learning again, what we were just reminding ourselves about. Suppose that v1, v2, v3 is Li. So if we have a linear transformation that is one-to-one, and we start with 3 linearly independent vectors, then the set of t of v1, t of v2, and t of v3 is still Li. Okay, so in other words, what we're going to show is that if you transform a linearly independent set using a one-to-one transformation, the resulting vectors that you end up with are still one-to-one, right? So you start with these 3 linearly independent vectors, you transform them, the resulting set is still linearly independent. And this is partially to review linear independence, but also we're going to need to use the fact that we have something that's linear and something that's one-to-one. Okay? It's not very long. This is a pretty short solution. Can somebody tell me, this is so incredibly important, what's the first line that I'm going to write down? Getting it started on the right footing is critical. Brandon?
The definition of Li.
Yes, so tell it to me.
C1, V1 plus C2, V2 plus C3, V3 equals 0 only when C1, C2, and C3 are 0.
Okay, so that's writing out the whole definition in general. Okay, but this is not really what I was looking for. So you're giving me the definition of what it means for V1, V2, and V3 to be Li. But in terms of doing this proof, so to speak, how would I want to start, I guess is my question. Do I want to start with these 3 vectors? Or do I want to start with these 3 vectors? In terms of my writing up my proof.
I want to start with the transform.
The transformed vectors, exactly. What I want to do is show, this is what I'm trying to show, right? I want to show that these guys are Li. So how do I do that? Well, I assume that C1 T of V1 plus C2 T of V2 plus C3 T of V3 is equal to 0. Now that is not, some of you might be thinking, oh, well, you just assumed what you're trying to prove. No. What I'm trying to prove is that if I assume this, then C1, C2, and C3 are 0, right? So we will show that C1 and C2 and C3 are all 0. That's right. Does that make sense? So the one-to-one definition is always so slippery because it's an if-then statement. So if we want to prove that some set of vectors is Li, I have to assume the if part of it, which is this part of it. Okay? if I want to prove that all Saturdays are sunny, first thing I'm going to have to do is be outside on a Saturday. If I'm outside on Tuesday or Wednesday, that's not going to help me prove that all Saturdays are sunny. I have to assume the relevant information. So here I'm assuming that these three vectors cancel out in a linear combination. And I'm going to try to show that the constants are 0. So this is the starting point. Which means, actually, so far, I have not touched this at all. And I have not touched this at all, and I have not touched this at all. Okay, so we have a lot of stuff that we can use. Does anybody have a suggestion, starting from the box, what I could do?
Yeah.
I'd love to hear it.
I'd like to move those C1s inside of the transformations.
Okay.
Each of the
Each of the coefficients, put them inside the transformation. I can do that because t is linear, right? So t respects linear combinations, right? T respects addition and scalar multiplication. So let's just take advantage of that right away. So since t is linear, right, we can put the t in front of everything. I'm not only going to move the constants inside, Brian, I'm going to actually move the plus signs in there as well. Right, just kind of do the whole shebang. Okay, so we got that. And now, so I've got that. So anybody have a suggestion of what I can say from there?
Since the transformation is 1 to 1, the only vector which t takes is 0 is 0. So this requires C1 B1 to be 0.
Okay, this whole thing inside here has to be 0 because t is 1 to 1. Let me just write that down so everybody's got it in their notes here. Since t is 1 to 1, right, the definition of that is that the kernel is trivial, right? There's only one vector in the kernel, and here you have a vector that is, by definition, in the kernel of t, right? And so that vector has to be 0. And so C1 V1 plus C2 V2 plus C3 V3 is equal to 0 since it's in the kernel, right? This just really says that this guy right here belongs in the kernel of t. Exactly. Right? So that guy's in the kernel of t. Okay, great. So we've got this equation. Now what can I do? I've used the fact that t is linear, used the fact that it's 1 to 1. Where can I go from here?
Well, your
So the one thing I haven't used, it's always a good clue, is that if you haven't used something that's given to you, you probably need to, right? So we have not used this part, right?
That part is literally what that's saying, with the added fact that C1, C2, and C3 are equal to 0.
Exactly. So since V1, V2, V3 is Li, right? Then what does it mean? Oh, it means that whenever those three vectors cancel out in a linear combination, all of the constants are 0. So we literally finished the proof with just one more line. That's the whole thing, right? That's actually what we will need. That says what we needed to show was that all of the constants are 0, and now they are. Okay, is that good? Okay. I'm just going to take a quick stock of where we're at with the review. There are 11 problems on this review packet. Of course, I did 2 extras at the beginning, 3 extras at the beginning that were from that quiz. So far, we've done number 1, number 2, number 3, number 4, number 11, and that is it. So, so we have about 6 more to go. However, I'm probably not even going to bother with number 7 because it's actually similar to the one that I did that was from the quiz, and it's really very easy, and there's a solution already online. Number 6 has a lot of parts. I'm not going to do probably all of those parts. What I'm going to recommend is I'm going to try and do number 9 and number 10 next, which are about linear transformations. And then 5 is a pretty easy one. It's a 2 by 2 linear system where I'm asking about the phase portrait. Okay, so I could go over that. And then number 6 and number 8 are both from chapter 8. So they have to do with annihilators, variation of parameters, kind of checking that stuff, which I think is the easier stuff usually for most people. So I'm going to save that till a little bit later.
How
Yeah.
long would the exam, how many problems would be on the exam?
How many, you know, take a look at the sample midterm and that'll give you a good idea. This is not, I'm not going over a sample test right now. I'm going over like just a slew of problems. But you can take the sample midterm. It normally I think my exams tend to have about 5 or 6 problems, but then there might be part A, part B kind of thing. So, and remember that as usual, I'm gonna give you guys a little bit extra time. You're welcome. I'm gonna give you guys extra time, like I always do. So hopefully it will not be so rushed. But anyway, yeah, I think what I'd like to do is focus on problems 9 and 10 next, and I think that would be, it's older stuff, so it might be good to go over it. We haven't really reviewed this lately, so let me look at number 9. It says define t going from m2 of r over to p2 of r via t of a, b, c, d equals a minus b plus d plus negative a plus b minus d times x squared. So I have a transformation. It's going to input a 2 by 2 matrix and output a quadratic polynomial. And what it's going to ask for is find bases for the kernel of t, the range of t, and decide if t is 1-to-1 onto both or neither. So we've seen these kind of questions before. So let's see if we can work through this whole thing. I'm not actually asking you to show that t is linear here. In other words, that it respects addition and scalar multiplication. We're going to assume that. If it didn't respect addition and scalar multiplication, then it wouldn't be linear and we couldn't talk about any of this, right? So this is all hinging on that assumption, which is fair to take, because showing that t is linear is actually not something I'm going to be asking you on this exam. That was actually from the last exam. So, but the kernel and range, these are kind of new. So where do you guys want to start with this thing? Do you want to start with the kernel? Do you want to start with the range? Or do you want to start with telling me something about the question at the end?
I want to say you cannot have both of these things because you have a transformation going from it's a 2-dimensional space to a 3-dimensional
Wait a
space.
sec, what's the dimension of M2 of R?
It is 2.
It is 4.
Oh, 4.
It is 2 squared, right? So this is a 4-dimensional space, and P2 of R is what dimension? 3. Okay, so I like your conclusion, which is that the dimensions are not the same, so it can't be both. And what else can it not be if V is bigger than W? 1-to-1, right? Yeah, so it cannot be 1-to-1. So this one is either onto or neither. So what you should do, guys, is you should explain just briefly. You can just say the dimension of V bigger than the dimension of W. So many times, I have taught this class so many times, and people will just cross things off with no words, like no explanation at all, and that's hard to give credit for because you could just be guessing for all I know at this point. So please, just put something. It doesn't have to be an essay. Just put like a little thing here, 4 greater than 3. If I see that and you've got it next to where you crossed off, then I can be comfortable that you understand what just happened. Great. Okay, so there we go. All right, Brandon?
Can we also cross up onto, because there's no way to get an x value?
Okay, you happen to notice something unique about this particular problem, which is that the range is not going to be all of P2 of R because there's no x term in what you're spitting out over here. You're absolutely right. I already know that it's not going to be onto, but that one is depending on the actual form of this particular transformation, and so you might not always have that quick, no answer on that part, so we should think about how we would really do it. Of course, to answer any of these questions about one-to-one, onto, both, or neither, knowing the kernel and range is going to be the ultimate, key to figuring that out, right? So where do you guys want to start? Do you want to start with the kernel, or do you just want to start with the range? Kernel? Range? Well, we're gonna do two problems, so let's do one of them one way and we'll do the other one the other way. I'll start with the kernel here. Okay, so let's do the kernel of T. Start with that. We need to remember how to find the kernel. What you do to find the kernel is you take your transformation on the left side and you literally set it equal to 0. Okay, and what this means is that a minus b plus d plus negative a plus b minus d x squared has to be 0. Now, when you have something like that, this is an equal sign, which means that the left side and the right side have to balance. What this means is that the coefficients, each coefficient of each term on the left side has to be 0. Sometimes I'll see people try to solve for x here, like use the quadratic formula or something. No. You're not trying to solve for what x is. The different powers of x are just the placeholders for the coefficients. And if it's all equal to 0 on the right-hand side, it just means that each coefficient on the left side is really 0. So what we actually get out of this is a system of equations. So let me write down that system for you here. System of equations. So the constant equation is just a minus b plus d equals 0. I'm leaving some space because I don't want you to forget that there really is a c as well. So I don't want to give up any room for that. The second equation is negative a plus b minus d equals 0. So there's my system. And I can, of course, try to solve now for a, b, c, and d. So you're just going back to chapter 2. When we first learned how to solve systems, you can put this into a matrix, 1, negative 1, 0, 1, augmented with 0, and the second row is negative 1, 1, 0, negative 1, and 0. This is the linear system in augmented matrix form that we're trying to solve. Obviously, the second row is just going to wipe out. It's just a multiple of the first row. And what I end up with here is a pivot and 3 free variables. Notice that it's 3 variables. Some people forget about the fact that the c is gone, but you really do have to include it. So I am going to use 3 free variables. I'll call them r, s, and t for b, c, and d. Okay? And the leading variable, the one with the pivot around it, has to be solved for. So if you look at this first equation that you have up here, a is just equal to b minus d. b minus d, which is just r minus t. Okay? So I'm now going to do something that is on purpose incorrect, and I want you guys to catch what I'm going to do wrong. The kernel of t is therefore the set r minus t, r, s, t, such that r, s, and t are real numbers. What's wrong with that?
We're talking about matrices.
Okay, the kernel is a subspace of V. What is V? It's 2 by 2 matrices. We just wrote down a vector that looks like it's in R4, right? And people do that very casually because it's the way we wrote these equations down. We wrote them in a column like this, so when people start thinking about busting out variables and so on, they tend to just write them in a column like that. But what I should have done is I should have written it into the proper form, right? Which would be that A is right there, R minus T, B is R, C is S, and D is T. So it's just the way you're representing it should look like the shape. If this is polynomials up here, then your kernel should look like polynomials, right? It's whatever the V is the shape of the vectors. So R, S, and T are real numbers. Okay, so my basis, I think people are pretty good at this by now. You just have to bust out your variables to get your basis. So what is my first basis vector going to be?
1, 0, 0.
1, 1, 0, 0, thank you. And the second basis vector?
0, 0, 1, 0.
0, 0, 1, 0. And the third one?
-1, 0, 0, 1.
All right, there you go. And what is the dimension of my kernel?
It's 3.
It's 3, right? Dimension of the kernel of T is 3. Now the nice thing about already knowing that up front is that I also now know what the dimension of the range is. Even before I start working on the range, I know its dimension.
It's 1.
Question?
We could do the opposite with the range too.
Yeah, so if we had started with the range and figured out what that was, we could take that dimension and we would know the dimension of the kernel. Maybe I should write it down. I keep waving my hands about it and talking about it, but I don't think I've written it down on the board once today. This is like super important. Dimension of the kernel of T plus the dimension of the range of T adds up to the dimension of the vector space V. So usually the dimension of V is something you'll know. Like I know that the dimension of M2 of R is 4. So that means these other two numbers, if this is a 4, these other two numbers have to add up to 4. So if this one's 3, then I already know that the range has to be one-dimensional. Does this make some sense? Okay, so the range has to be one-dimensional. Okay, so let's look at that range. Do you remember how to find the range?
Take the column space.
Okay, that's if there's a matrix. So if we, okay, so let me be clear. If we have a transformation from Rn to Rm, which we don't right now, but if we had this kind of transformation, then in this case only, the kernel of T is the null space of whatever the matrix is. So there would be a matrix here, sorry. There's a matrix that would facilitate that transformation. It would be an M by N matrix, and the kernel would equal the null space, and the range would equal the column space. So this is a great thing to know, and in fact, this was what I think I asked you on the quiz. I had some question with an actual transformation like this. So for this type of transformation, yeah, you just take the matrix and find the null space and column space, and you get your kernel and range. However, the problem that we are working on right here is not from Rn to Rm, and so what is the procedure for finding the range in sort of a more general situation? Span of, is that what you were going to say?
The span of the basis, or the transformation of my basis.
Okay, the span of the transformation of a basis for V, right? So we take a bit, and I'm sorry, I kind of lost my, here's V, right? It's the 2x2 matrices. So what would be a good basis for M2 of R? So you've got to come up with some 2x2 matrices, right? So this would be a nice one, right? And then maybe this one, right? And then maybe this one. These are the standard matrices. Okay, so you could say, all right, I'm just going to take the span of those 4. Now this is a list of 4 things, but I can already tell you before I even calculate them that those 4 things are going to be all multiples of each other, because the dimension of the range is only 1. So these cannot be Li over here, or we would have a big problem, right? So they're all going to be multiples of the same thing. Let's just figure it out. Let's plug in, let's figure out what is t of 1, 0, 0, 0. It means I'm going to put a 1 everywhere I see the A, because the upper left corner is representing the A position. So A is 1, B, C, and D are all 0. So if I plug that in, I'm going to get 1 minus x squared. I need to make sure everybody's understanding how I'm getting this. So if I plug in 1 for A, 0 for B, 0 for C, and 0 for D, does everybody agree that I get a constant term of 1 and a coefficient of x squared that's negative 1, which gives me this one, right? The second one I have to evaluate is t of 0, 1, 0, 0. So for this matrix, the B is in the 1 position, right? So I'm going to put a 1 everywhere I see a B. So I'm going to get negative 1 there, and then plus x squared. Okay. T of 0, 0, 1, 0, well, I have to put a 1 everywhere I see a C. And I put 0 for everything else. Well, I don't have a C up there, so I'm just going to get 0. And lastly, when I plug in a 1 for D, I get 1 minus x squared again. And so, was I not right? All 4 of these are just multiples of the first one. Now, if it wasn't obvious to you that they were multiples of each other, you could check them for linear independence, right? You could like lay them out in the columns of a matrix like we used to do in chapter 4. Row reduce it, right? You're only going to get 1 pivot. And it's going to be right in that first column, which means this is going to be your basis right here. Right? In this case, you can take the transformation of any basis that you want. So I put a question on last year's exam where, and it's in the sample test, so you guys will get a chance to try it out. I put a question in last year's, the last time I taught the class, where I don't remember the exact question, but it was I really liked the question, where I didn't have a formula like this, but instead what I did is I told everybody, okay guys, t of 1, 2, 3, 4 is 3 plus x minus 2x squared. And then I said, and t of 5, 6, 7, 8 is something else, right? And I created a specific set of values here. I think I came up with 4 of them. I know these aren't the right I know these aren't the right vectors, but the idea, I'm just trying to give you the idea. So I did not give the class a formula like this, right? If I had given a formula like this, sure, you should just pick the easiest possible basis on Earth. But instead of doing that, I said, all right, I'm not going to give you the whole formula. I'm just going to tell you a little spotty information about t. Here's what t does to this particular guy, this particular guy, this particular guy, and this particular guy. And the idea was that what the students were supposed to do when they were calculating the range is not choose 1, 0, 0, 0 and 0, 1, 0, 0 and so on, normally the best basis to choose. No, they were supposed to choose exactly what I gave them right here. I basically handed it to them on a silver platter and said, here you go. And you just transform these guys. And of course, I already had the answers right here. And that was the list. And all that the students had to do on that problem was check that these are Li. Okay, so that would be a slightly different version of the same kind of problem. And it is on that sample test. So if you go back and do the sample test before Monday, I really recommend that. You'll see kind of another example of practicing this stuff. Okay, are we good on this? Yeah, go ahead.
So if we started with the range, and we wanted to figure out what the kernel is, we're gonna look at, we're gonna just augment
The first thing is, if you start with the range, if you started with the range, then in theory, you don't know the dimension of this yet. So you might not be able to assume that you can cross 3 of these off. Remember, we already knew that the range was going to be one-dimensional here because of our dimension theorem up here. So I already knew that although there's 4 things listed here, it's only one-dimensional, right? So I was able to just be pretty loosey casual and cross 3 things off. But if I didn't know the dimension of the range, I would need to actually put these into the columns of the matrix, row reduce it, and I mean, you can still see it, obviously, that these are all multiples of each other, but let's imagine you didn't see that. Like, let's say you have a bunch of things listed here, and you're like, I don't know. Right? Well, you've got to put them in the columns of a matrix, row reduce it, and then throw away those vectors that are corresponding to unpivoted columns, right? That's the way we did this back in chapter 4. Just keep the pivoted columns, and we'd only have 1. So you'd figure this out first. How does that help you with the kernel then, if you do this first? Well, you'll know that if you did this part first, you'd know that the range was one-dimensional. Now you could use the equation in reverse to say that the kernel is three-dimensional. But you're still going to need to calculate the kernel, kind of the way we did before. Right? So
It kind of makes sense to start with the kernel.
well, I mean, it's really up to your preference. Like, I don't know that I could say one is better than the other. In fact, on this next problem, I want to try it the other way around. But yeah, so that's kind of the idea. Let's do one more of these, which is number 10 in the review packet here. So number 10 is to just do the same exact thing for a slightly different transformation. So T goes from P2 of R to P2 of R via T of P of X equals X times P prime of X plus 2 times P double prime of X. And I would like to figure out whether this is one-to-one, onto, both or neither, and I would like to figure out whether what the bases are for the kernel and for the range. Okay? So first of all, on the one-to-one, onto, both, and neither thing, let's just write that down. Can we cross anything off right away? Okay, because the V and the W are the same size, they're both three-dimensional, your transformation is either both or neither. Okay, it just all depends. Okay, it's either both or neither. So let's do the range first. This time we'll do the range first, just to practice how that would look. So this is going to be the span of the transformation of a basis for P2 of R. Can you give me a good basis, an easy basis? You get to pick it. A good basis for P2 of R, Troy?
A plus B.
So I want polynomials.
So A plus B, and then so the A would have an X and the B would have an X squared.
Okay, so like that.
Mm-hmm.
That's not a specific polynomial though. I want like a specific one, you know what I mean? Like I don't want A's and B's in my... So the form of P2 of R would be ax squared plus bx plus c, right? It's like all possible quadratics, but what would be like a basis for it? Like how would you write, like what would be, if you were going to like express 3 specific polynomials for the basis, what might you give me? Yeah, just plug in 1 for A, B, and C. What are you going to get?
X squared plus X plus 1.
You're going to do, no. You're going to do them individually, one at a time.
Oh, okay.
So when you plug in 1 for A, what do you get?
1.
X squared. Okay, when you plug in 1 for B, what do you get? X. When you plug in 1 for C, what do you get? 1. Okay, that's what I was looking for. The standard basis for P2 of R, right, is X squared, X, and 1. and we have to transform that. So t of x squared, t of x, and t of 1. Okay. Again, you can use any basis for P2 of R, but this is probably the easiest one that anybody might think of. Okay, so we have to work this out. I have to transform each of these things. Let's transform x squared first. When I transform x squared, what is my formula saying? Well, it says take x times the derivative of that. So you're going to take x times the derivative. What's the derivative of x squared?
2x.
2x. Great. And then plus 2 times, what's 2 derivatives of x squared? 2. So we have 2 times 2, which is 4. Okay. So everybody with me? And then I have to do t of x. So the formula is x times the derivative of x. Well, that's just x times 1. Plus 2 times, well, 2 derivatives of x is just 0. So there's nothing else. Okay. And what's t of 1?
0.
You're not going to get anything, right? Because by the time you take derivatives of everything, it's just 0. Okay. So in other words, what we have here is the span of 2x squared plus 4, comma x, comma 0. Are these three results my basis?
No.
They are not, because why not?
Because 0 is always linearly dependent.
Right, these vectors have to be checked for being linearly independent. We know they span the range. We got that down already, but they have to be Li, and 0 will never be Li. So we gotta cross that one off. Once I've crossed that one off, what about the other two?
They are Li.
They're pretty good, aren't they? Once you have only 2 vectors, it's usually pretty easy to tell. Right? 2 vectors will be Li if and only if they're not scalar multiples of each other. So these 2 right here form your basis. So there's your basis. And so what is the dimension of the range? It's 2. So is my transformation going to be 1-to-1 onto both or neither? I mean, the dimension of these 2 spaces is 3, right?
Neither.
So, right, it's not onto, because the range is not big enough, right? If it's not onto, then it's actually going to have to be neither. Yeah.
So when you have matrix, well, not, I don't want to say, when you have a matrix defined linear transformation.
Like this, yeah.
Right, and it's n is equal to n. You could just take the determinant, right?
That's true, yeah.
If you have something like this, could you say, well, I'm gonna, whatever transformation is gonna go on here, I'm gonna put that into a matrix, or no, that's just, you could do it, but just...
You will learn if you take Math 307 that you can associate a matrix with this transformation and take the determinant of it, and it will be a 3x3 and it will give you the right answer. I don't want to do that at this stage, if that's okay. We can go in that direction, but it's a little more, like, we have to be careful how we do that. So, for right now, if we don't have this kind of a setup, there's really no matrix over here that we use. Okay, based on what we've said so far, can you tell me what the dimension of the kernel is going to be? Without even doing the kernel, do we know the dimension of it? Dimension of the kernel of T, right? What's it going to be? 1. Right? Because 1 plus 2 adds up to 3, which is the dimension of P2 of R. So I know that the kernel is 1-dimensional. Now let's see if we can figure out what the kernel actually is. Okay. Trying to figure out what the kernel actually is. Okay. So how do we find the kernel again? Sorry? Right, so in other words, T of P of X equal to 0. you're going to kind of set that equal to 0, you're going to solve for p of x. Now, the t of p of x is just x p prime of x plus 2 p double prime of x. So we're setting that equal to 0 essentially. Now, the problem with this is that this is actually a differential equation that is second order and does not have constant coefficients. So it's actually an equation that we have not learned how to solve. We have actually not studied this anywhere else in the semester. So I'm a little worried now, like how am I going to actually figure out what is p of x? Anybody have an idea what we're going to do here to actually figure out what p of x is? Remember, p of x is going to be in V. It has to be over here in the P2 of R, right?
Just like subtract, you know, go ahead and like subtract one of the sides. No, because you have that x coefficient.
That x coefficient is really the problem. I mean, if we didn't have that, we might be able to like use some of the chapter 8 material. Right, we would write down an auxiliary equation and actually solve the differential equation. But that x in front of it is what throws a wrench in that whole strategy. And I know we've been talking for like 2.5 hours, so we might be getting a little tired too. This is not a totally trivial thing. Do you have an idea, Brandon?
So since p is a polynomial,
Yes.
you can write it in its abstract form, right? A, B, and C, and differentiate it, throw that x in there.
That's the answer. Because we're not trying to solve the differential equation sort of for arbitrary functions, but specifically for a polynomial, what we need to do here is literally write it as an ax squared plus bx plus c. It is, after all, in P2 of R, right? If I'm willing to do this, I'm pretty confident I'll be able to take derivatives and solve it out, right? So like p prime of x, right, and p double prime of x, these are going to be easy enough things to come up with. So the derivative is 2ax plus b, and the second derivative is 2a. All right, so that's pretty nice, and now I can plug that into the left side of this equation, right? So what we're going to get over here is x times 2ax plus b plus 2 times 2a equals 0. Okay, so I just put in the polynomial with it expressed in terms of the a, b, and c. So this is important to recognize that you can do this. You really need to do this here. If I multiply this out, I get 2a times x squared plus b times x plus 4a equals 0. And again, we have a left side equal to a right side. This right-hand side where I see a 0 here, I want you to think of that in the polynomial world as 0 times x squared plus 0 times x plus 0. And I can now match up the coefficients, right? I can match up the scalars in front of these things. Right? Each term has to kind of line up. So we know that 2a has to be 0, b has to be 0, and 4a has to be 0. So we get what?
A equals 0, B equals 0.
Great. A equals 0, b equals 0. Oh, there is a c, isn't there? Don't forget that there is a constant in the polynomial. So that's free. I might call that t. So then to do my kernel, do I just do this? A lot of people do. You guys are on top of it because we've been emphasizing this. Do not write it like a vector in R3. Write it like a polynomial. But as a polynomial, it would literally just be 0x squared plus 0 times x plus t times 1, and that would just be t. So this is my kernel. I shouldn't be writing that far over there, not everybody's gonna be able to see that. So 0 times x squared plus 0, this is my kernel, guys, plus 1 times t, right there is the kernel of my transformation. And that literally is just t, and a basis for that is what? After I bust out the t, what's left? 1. And that fits because it's supposed to be a one-dimensional kernel, right? Actually, the kernel is just all constants, which makes sense. If you plug a constant into here, you clearly get 0 when you differentiate. Actually, that would be the other way to do the problem. Say, oh, I know what the dimension is. It's only one-dimensional. I just need to find one thing that actually solves the equation. And maybe by luck, you happen to notice, oh, if I take the derivative of any constant and then plug it into the equation on the left side, it becomes 0, right? So you could just do it that way and you'd be in pretty good shape. Okay, does that make sense? All right. Any questions on one-to-one, onto, kernel, range, the relationship between them? Remember, I've got some videos. This was the week I was gone. We came, we had some videos for you to watch to kind of put this all together. You're going to see it in the sample test, a little bit more chances to practice it on something you haven't quite seen yet. All right, I think trying to decide if I want to do, so I've got 3 more of these that I haven't gone over yet, but I don't know if I'm going to do all of it. As it's about 7:30, I'm going to imagine that everybody's getting a little tired. I used to do these review sessions when I was like 20-something. I was a little younger as a grad student, and we would go for hours. We would show up, like, I don't know what time it would be, but nobody would leave. Like, I would talk and talk and talk, and everybody was like, oh, I can't leave because the minute I leave, he's going to say something that's going to be on the test. And I wasn't even writing the tests back then. I was just helping the students and the professor. This was before I was a professor. I was just, like, doing my best to, like, try to help people out. So people would come, and, we would literally, like, have to stop and go, like, everybody would go take, like, a dinner break and come back and, like, go, like, for 4 more hours. And it would end up being, like, the middle of the night. And people would still be there. This was when I was younger, and I could actually handle it. These days, I tend not to want to do that. But yeah, I swear, if I wouldn't have eventually stopped and said, okay, I think I've done everything, I think everybody would have just stayed all night. The thing would never have ended, because people were really, really focused into it. Let me see.
So were you like a tutor?
Yeah, I was like a TA. Yeah, so like I was the good guy. Like I was the one like helping the students and trying to do. And the professor didn't show me the exam, so I had no idea what was going to be on it. It's like, I'm just going to do everything I can to try to help you guys out. Here's all the questions I can think of, and it just went on and on and on and on and on and on. And then, so I looked like the good guy, and then everybody hated the professor instead of me. Now it doesn't quite work that way, although I try to treat it the same way because I didn't write the test yet. So I'm trying to just, be totally open and candid as much as I can.
It's hard to hate you when you put this much effort into a review section.
It's okay.
No matter how hard the test is.
I do enjoy doing this stuff. Let me tell you what we have not reviewed, and I'm going to ask you whether you want me to. I think I've reviewed what, for me and for my experience, is the hardest stuff for the students. Let me tell you what I have not gone over. I have not reviewed the annihilator method for solving non-homogeneous higher order differential equations. I have not, which I'm going to give you a table for that, right? I have not reviewed variation of parameters. So these are the 2 main methods, and this was in chapter 8, and we just did this pretty recently, so I'm hoping it's somewhat fresh. Make sure you know the formulas on the variation of parameters, right? There's 3 formulas. You have to know the form of the particular solution, which is u1, y1 plus u2, y2, right? And then you have to know the formulas for u1 and u2. And most people know them pretty well. There were a few people on the quiz that did not get this one right. So there's a negative y2f over the Wronskian that you're integrating for u1. u2 is similar, but there's no negative in front of it. So it's just the integral of y1f over the Wronskian.
So chapter 8, the Wronskian is just your
y1 and y, so the Wronskian is the determinant of the matrix you get when you put your y1 and y2 up here, and you just take derivatives down the matrix.
And how is it different from the one we use in 9?
Chapter 9 Wronskian has no derivatives in it, because you're already building an entire column of that determinant matrix out of the vector solutions. Remember, chapter 9 is all about vector solutions. So, and there's some group work where I kind of walk you through how this Wronskian verifies linear independence and everything else. That's all really in chapter 9. But yeah, so you just have to calculate this little Wronskian, put it on the bottom of this thing here. Was there a hand up somewhere? Yeah, Aaron?
And those are only for two by twos, right?
This is, well, variation of parameters is only for second order differential equations. If that's what you mean.
Yeah.
Yeah, so if the differential equation is higher than second order, then you are not going to be able to solve it using variation of parameters. At least I will not ask you one that's like that. By the way, that reminds me, in my 207 class I remembered to do it, but in 250B I did not. There was a group work here. I'm just going to pass this out to you guys. You already have it. Could you pass that back for me? And could you just give that back to Eric? This is group work number 15 that we did not have time to do in class. But for example, actually let me just pass this to everybody. I have a lot of copies because I want to say something about it right now. If you look at problem number 2 on this group work number 15, so you can try these on your own because we didn't get a chance to do them. But problem number 2 says discuss how you would solve these differential equations. So there's y triple prime plus 3y double prime plus 3y prime plus y equals 2e to the negative x plus 3e to the 2x. Right? So, for example, what's the order of that differential equation? It's third order. So you know that I'm not going to be asking you to solve it with variation of parameters, right? Variation of parameters is only something I will ask you for a second order equation. So what method are you going to use to solve this? Annihilators. Exactly. So, you know, you have to start with the complementary function. You see the auxiliary equation here is actually pretty nice. There's your auxiliary equation, r cubed plus 3r squared plus 3r plus 1. If you factor that, this one factors as a perfect cube. It is actually just r plus 1 quantity cubed equals to 0. So your, if you were to expand out r plus 1 cubed, you would get exactly this auxiliary equation right here. And what this tells you then is that the roots are -1, -1, and -1, 3 times. Right? Because there's 3 factors of -1 when you write this out 3 times. And so from there you can write down, so I guess I'm going into this a little bit here. Again, everything that I'm either doing or not doing here tonight, I have solutions for. That's the other thing. Back when I was a grad student TA, I wasn't quite as organized with my materials as I am now. So I didn't have all these handouts with solutions to everything. So it's like everybody needed to see the solutions in real time. Now, of course, you can look at the stuff. But anyway, so the complementary function here would be what? If my roots are -1, -1, and -1. C1 e to the negative x. C2x e to the negative x. There you go. So is everybody understanding how, you know, you handle repeated roots and complex roots that might come up to the auxiliary equation? I usually will ask one on this midterm that's like about a 15th order differential equation, and right? And I just really make you work it out. Like it takes longer to write the answer than to solve it. You just have to figure out all the roots, and I'm really just testing whether you understand how to do all the stacking of x's and the stuff that involves complex roots. It's not that hard, but you know, it's sometimes I give you a little bit of a bigger one, just to really test it. Okay, great. So then once you've done that, then you look at what's on the right-hand side. Well, you have to figure out annihilators here, right? So the annihilators comes into play. What's the annihilator? I know I'm going to give you a table, but maybe you already know. What is the annihilator of e to the negative x? A of d equals d plus 1. Okay. Does the 2 make a difference? Not at all, right? What about the annihilator of 3e to the 2x? D minus 2. And does this 3 make any difference? Not at all. And what do I do with these two separate annihilators that I have here?
Multiply them.
You multiply them. Very important. Even though this is a plus here between these two, right? If you have separate terms with pluses and minuses between them, you have to multiply the individual annihilators. So your overall annihilator for this one would be d plus 1 times d minus 2. And you can just take that and write down the new roots that result from applying this annihilator to your differential equation. And what are those new roots going to be here? Negative 1 and 2. It's just that simple, right? And then when you're writing down the particular solution, remember that you're just going to continue building off of what you had already put in your complementary function. So notice that the negative 1 is showing up again. So since I've already done 1, 2, 3 terms of that, the next time I write down negative 1, I'm going to have an x cubed in it. And instead of calling this term C4, I would use a different letter like a. So ax cubed e to the negative x would be a good choice. And then the second term would be b times e to the 2x, right? And that's not a repeated root, so we just express it just like that. Okay. Now, what I have written right here, guys, is what is called the form of the particular solution. So if I ask you, this is a mistake I've seen people make in the past on this exam, is they actually keep working on it, even though if I say, just give me the form of the particular solution, that's all you have to do. So what you would do is put a circle around your complementary function, right? Put down the form of your particular solution, and then your final answer here would be y of x equals y sub c of x plus y sub p of x. So you would add together those two parts. Yeah, Brian?
But don't we often solve for the A and the B?
Right. So if I only ask for the form, though, this is all you need to do.
Oh, so the form is...
It's just with the A's and B's in it, without solving for them.
Oh, so...
Like this is the form. We're done with finding the form. Now here's the thing, guys. If I don't say that, let's say I don't say find the form. What if I just say very, very broadly, find the general solution? If the question says find the general solution to the differential equation, then this would not be good enough because we haven't figured out A and B yet. To figure out A and B, what do? You take this form and you plug it in on the left side of the differential equation and match it up with the right side. Now, that's going to mean you're going to have to take some derivatives of this. And you can already see the product rule is going to be required for that. And you're going to have to do 3 of those derivatives. That's probably more than I would ask you to do. What I want to say to you is there's a decent chance I will ask you to solve for some constants on a problem somewhere. But here's the thing, it's not gonna be worth a huge amount of points. It's pretty easy to make an error. It's pretty easy to, with the product rule and all the sign changes and stuff, by the time you've taken 3 derivatives and tried to group it together, it can happen that you might make a little mistake. I would recommend, don't like miss 20 points at the end of the exam that you could have worked on because you spent a half hour trying to figure out what A and B are here, which is probably gonna be worth like 2 or 3 points or something, right? So be smart about this, okay? This is not such a big deal to solve for the A and the B. If I'm gonna ask you to do it, it will probably be on a relatively easier problem from a calculational point of view. But if I ask you to do it, it's also not gonna be worth that many points, okay? So that's my advice about that. More important thing is, know the 3 steps, right? Know how to write down the annihilators, all that good stuff. Right? That's gonna be important for you guys to be able to do. I have one more thing I wanna do. Is this good though? We good with this, or am I just gonna leave it like that? So that problem is fully solved in the group work, so you can look at if you wanna continue, you can look at the answers. But I wanna say one more thing. And maybe I'll skip the variation of parameters because it's so technically simple. I mean, it's just, you'll have a table of integrals, you'll have to do a couple of integrals, but it's not very conceptually that difficult. So maybe I'll skip going over any of that stuff. You can look up any of these that I didn't do online, but I do want to say one thing. Suppose I ask you this question here. This is actually off of the review packet number 5. Consider x1 prime equals negative 6x1 plus x2 and x2 prime equals 6x1 minus 5x2. I'm going to ask you a few just quick questions about this. Okay, the first one is, what is the fundamental matrix? Kind of want to review what that means. So what is the fundamental matrix? Second question is, find the general solution. And then the third part is going to be to draw the phase portrait. Okay, so I did not actually put this system in a matrix to begin with. And that's because I'm actually asking you how to do that. So in other words, I wrote them out as 2 separate equations. I could have written it, I think hopefully everybody recognizes that we are talking about a chapter 9 scenario. It's a linear system of differential equations. I could have just given you the matrix. I chose not to do that. I'm going to make you write it down because I want to make sure that everybody can do it. So if you know how to do that, what is the matrix here? What is capital A?
It's negative 6.
Negative 6 and 1.
6
And 6 and negative 5, and that is absolutely right. I have people that try to do things like take a transpose, or they'll put rows and columns reversed, right? Or they'll do something else like take an inverse or whatever. No. Right? The coefficient matrix is just this. Now, is this the fundamental matrix? No, the fundamental matrix is something totally different. This is just setting it up. This is just saying, all right, I want to take what Dr. Annan gave as the question right here, and I want to write it as x prime equals ax, because he didn't give it to me this way. So what you do is you just say, well, here's the matrix now. Okay. So if I give you a system of equations, but I have not put it into a matrix to begin with, you have to do that. It's probably not what the question's asking you to do, but you need to do that in order to start solving the problem. Right? So now the fundamental matrix, do you remember? That's a word that I mentioned it, defined it, but I didn't really use it very much.
It's got the solutions in it. It's got the x.
That's
you
it.
just multiply a by x. Isn't that what it is?
It's the solutions to the linear system, which I'm going to call x1 and x2. And so we have to actually do some work to get that. Did you have a question there, Troy?
You couldn't just set it up as x prime is equal to a times x1 and x2 next to the a?
No, because, well, it is true that the x1 prime will be equal to ax1. That is true. And this will also be true. But the whole shebang of this question is going to be to figure out what is x1 and what is x2. In other words, we're just going to solve this one, like we were doing much earlier today in the review. This is actually not a very hard one to do. The eigenvalues are, going to be pretty simple to get, right? So you're just going to do, how are we going to do this? We're going to take the determinant of negative 6 minus lambda, and 1, and 6, and negative 5 minus lambda, right? We're going to have something like that, and if we work this out, negative 6 minus lambda, negative 5 minus lambda, and then minus 6, we're going to get, lambda squared plus 6 lambda plus 5 lambda, which is plus 11 lambda, and then plus 24. Okay, and that's going to be set equal to 0, right? So this is my characteristic equation. Does this thing factor?
3 times 8.
So what's the factorization of the characteristic polynomial, though?
Lambda plus 3.
Lambda plus 3.
Lambda plus 8.
And lambda plus 8. So what are my lambdas? Negative 3 and negative 8. So just real quick, I'm going to jump ahead. What is the type, the classification type of the phase portrait?
They're both negative, they're both real.
It's so it's either a saddle, a source, a sink, an unstable spiral, a stable spiral, or a circle. We need to learn this. Remember that if there's complex numbers, that's when you get the circle. That's when you get the spirals and the circles and stuff. So there's no complex numbers here. So these are going to be 2 real solutions, and they're both negative. It's a sink. That's exactly right. It is a sink. Okay, so this is going to be a sink, and I'll come back in a minute and we'll actually draw a picture of it. Okay. So now we just have to take each of our lambda. Oh, let me not work on this board. Come back over here. Let's take each of those lambdas and just figure out the corresponding eigenvectors. This will only take a minute. We're just about done. Okay. So with lambda equal to negative 3, we're going to look at the null space of, I have to add 3 to the main diagonal of the matrix, so I'm going to get negative 3 and 1, and 6 and negative 2. And as usual, I can cross off a row, and I can use my little trick where I swap the 2 entries and change the sign of one of them. Okay, so what I get for my x1 of t is just e to the negative 3t times the vector 1, 3. Right? That's the first solution. And then I'm going to do a similar thing with negative 8. I take the null space of the matrix that I get when I add 8 to the main diagonal. This is going to be 2 and 1 and 6 and 3. And again, cross off a row. You have to be able to do that. And then I'm just going to do my little switching the positions trick and putting in a minus sign. So I'll put in a negative 1 and a 2. And I'll make my second solution, which is e to the negative 8t times the vector negative 1 and 2. Make sense? So my fundamental matrix, now I can answer all these questions pretty fast, right? My fundamental matrix, I used to call this just capital X. I know we haven't mentioned it a lot, but all it is it's a matrix, so it is definitely not just this matrix. I've seen people do that before. This is the coefficient matrix of the original system. What we've got to do here is put these two solutions. It's just what Brian said. We've got to put these solutions into the columns of this matrix. Now how do I write this as a column? The best way to do it is to just put the e to the negative 3t inside the vector there. So you'll get e to the negative 3t and 3e to the negative 3t. That would be the first column. And then similarly for the second solution, I would have negative e to the negative 8t, and I would have 2e to the negative 8t. We're actually, believe it or not, we have one more section of material to cover. On Wednesday this week, we're going to have to write down the fundamental matrix quite a bit for that. Okay, so that's the fundamental matrix. If you put them in the opposite order, it's okay. Right? It'll still work. And this is an invertible matrix, but you don't need to do anything with this other than just write it down. To get the general solution, we're pretty much ready to write it down, aren't we? The general solution is simply C1 times the first solution plus C2 times the second solution. And I would write that as x of t. This is little x of t, not matrix x, right? So C1 times e to the negative 3t times the vector 1, 3 plus C2 e to the negative 8t times the vector negative 1, 2.
And you can combine these if you want to.
You absolutely could do that, yeah. You could put, if you wanted, you could write this as C1 e to the negative 3t minus C2 e to the negative 8t. And the second slot would be 3c1 e to the negative 3t plus 2c2 e to the negative 8t. Not necessary, but that would be correct. Now, if you were to drop a feather onto the ocean whose currents were creating these solutions, at time 0 you drop the feather somewhere and watch the time flow to infinity. As t goes to infinity, all of these exponentials are negative, which means that your feather is going to drift straight towards the origin, no matter where you started from. That's why it's a sink, right? It's going to be a sink because no matter what the initial condition is, this thing is going to float towards the origin. So the phase portrait, the last part is to draw the phase portrait. It's really just a picture of it's a two-dimensional picture. Remember that usually the saddle is a little more interesting picture, right? The idea here is more or less, you can draw if you want, you can draw these eigenvectors. Here's 1, 3, all the arrows are coming straight towards the origin, also from the opposite side. And then negative 1, 2 is right here, but all of these arrows are also converging towards the origin. So remember when I did this in class with a saddle, right? I drew these 4 curves first, and then I just said, look, if you put the feather anywhere else, you're still going to get this feather going towards the origin, right? Over time. This is the way a picture of a sink would look. And the details of the actual trajectory is not something I'm going to be asking you to be able to do other than for the eigenvectors themselves. Right? So these other ones are not necessarily straight lines. If they were, then you would have every one of those other vectors would be an eigenvector again, which is not the case. So it's roughly this kind of a picture for the phase portrait. I'm actually not very likely to ask you to draw one because if I do, I'm going to get 50 different pictures that are. And it's like, well, how do I make it clear which curves to draw? And what would be more likely, if anything, would be if I could give you a matching exercise. I'd give you like 4 or 5 phase portraits and then 4 or 5 matrices, and I say, well, which matrix creates which phase portrait? I've never done that before. It might be a good idea. And you could just find the eigenvalues for each of the matrices, and then you just have to remember, you know, which case goes with, you know, which type of shape, you know. This is pretty simple, the 6 scenarios, you just have to learn it. You have to know, when is it a source, when is it a saddle, when is it a sink, when do you get a spiral, when do you get a circle, that kind of stuff. But we haven't done a huge amount with it. So that was number 5. So I've done everything almost on here except a couple. I haven't done a variation of parameters today, but I've done almost everything else. So I'm kind of thinking of calling it good. And then of course you guys can look at the solutions, and if it's not clear, you can come ask me. I'm gonna take a break, go get something to eat. I'm gonna come back later tonight. I'm gonna be here tomorrow, pretty much all afternoon and evening. I'm here for you guys. I want you to do well. I want you to feel comfortable. Feel free. My office space, even when they lock the building, call me in the office. I'll come let you in. Okay. Yeah, thanks guys for coming today, and I'll see you all again very soon. See if I can get this turned off correctly.